Imagine you're faced with a puzzle, but this puzzle isn't static, it's evolving. As you start to piece it together, you realize that each step you take transforms the puzzle, revealing new challenges and opportunities. Logical thinking in programming works the same way. It's not just about finding where pieces fit together, it's about anticipating how the pieces interact to change the bigger picture as you progress. Let's dive deeper into how logical thinking can help you not only solve, but also adapt to the complex challenges of writing and debugging code. In this video, we'll connect logical thinking to practical programming tasks. Recall that logical thinking in programming refers to the process of applying systematic reasoning to define a problem and arrive at a solution. Within the context of programming, developers most frequently use two primary logical thinking skills: deductive reasoning and inductive reasoning. Now that we've established the connection between logical thinking and programming tasks, let's dive into real-world scenarios. By exploring these examples, you'll see how developers use logical thinking to tackle common challenges in their work. We'll start with a situation where you would use deductive reasoning to solve a common programming issue. Imagine you're debugging a function that is supposed to calculate the square of a number, but it is returning incorrect values. The best place to start would be to identify where the function is likely going wrong. And in this case, you could start with the general principle that the square of any number should be that number multiplied by itself. Based on this general principle, you can then apply deductive reasoning to hypothesize that the issue most likely lies with a specific operator within the function. Further investigation shows that instead of using a multiplication operator to multiply the number by itself, the function is incorrectly using an addition operator to add the number to itself. The final step would be to test your hypothesis by modifying the suspected part of the code with the correct operator and then thoroughly testing it with a variety of inputs to see whether the issue is resolved. By using deductive reasoning, we identified and resolved an issue in a function. But logical thinking isn't limited to fixing bugs. It's also vital in improving performance. Next, let's turn our attention to a scenario where inductive reasoning helps optimize an algorithm. Imagine that you're working to optimize an algorithm to speed up its execution. You could start by analyzing the algorithm's performance, and doing so reveals repeated instances when the algorithm slows down while analyzing large data sets. Next, you would apply inductive reasoning to focus on the specific causes of these drops in performance. On closer examination, you discover that each time the algorithm processes a new record, it rechecks all the previous data it already processed, which is a redundant and unnecessary step, thus causing a systematic drop in performance. Finally, you would refactor your code to optimize these operations. In this case, you would rewrite your code to eliminate the redundant checks and then test for improved performance. After optimizing an algorithm, the next logical step is ensuring that new features integrate smoothly into your codebase. Let's explore how logical thinking guides the design process and ensures seamless integration. Imagine you're adding a dark mode feature to an existing mobile app that already has a settings menu where users can change preferences. Your first step would be to clearly define requirements such as the design and placement of the settings UI, the workflow for selecting and toggling the settings, the color palette and icon selection, and so on. Next, you would use deductive reasoning to determine how the new feature will interact with existing components based on the general principles of your codebase. For instance, you know that in the current app, any setting that a user changes is saved into app settings file. Therefore, the new dark mode setting will need to be added to this file so that when a user selects it, the app can read this preference from the settings and apply it into the UI. Finally, you would implement and test the code for the new feature to ensure that it works as expected within the existing system. For instance, after updating the settings file and application logic and modifying the UI to support dark mode, you would test the apply theme function to ensure it toggles modes correctly, manually switching between light modes and dark modes to ensure that the UI updates as expected, and verify that saved theme preferences persist across app restarts. By applying logical thinking, you've successfully designed, implemented, and tested a new dark mode feature that integrates smoothly with your existing application. You've seen how using logical thinking in debugging, optimizing, and designing features helps break down complex problems into manageable parts. The systematic approach not only simplifies problem solving, but also enhances your ability to create efficient, reliable solutions. This approach leads to writing clearer, more efficient code, debugging more effectively, and ultimately building more reliable software. In this video, you learned how to connect logical thinking to practical programming tasks. As a programmer, you can practice logical thinking by consciously integrating inductive and deductive reasoning into your everyday programming tasks. Doing so will help you tackle any challenges as systematically and efficiently as possible.
My name is Paul Party, and I'm your instructor for this course. I've been programming computers since I was in my teens. I love programming because it's like solving puzzles while designing and creating something amazing. My graduate degree is in philosophy, where I learned how to become a better thinker. When I program computers, I can apply many of the logic skills I learned in philosophy. Computer programming not only enables you to build cool software, but I believe it can help make you a better thinker. I started my software development career at Microsoft when the internet was just getting started, and I participated in the internet revolution firsthand. I managed software engineering teams that worked on desktop and web-based software. The internet gave software developers, particularly those working on user interface, incredible new opportunities. From mobile interfaces to websites, software developers are not only creating software that's functional, but also works of art. In my career, I managed and worked with teams at both Microsoft and PayPal that focused on customer-facing interfaces and learned how to make them great. I also spent part of my 20 years at Microsoft in training organizations where I learned how to communicate challenging ideas to new learners. I also was fortunate enough to have spent 15 years teaching non-majors philosophy at a university in Seattle. This reinforced my ability to teach learners difficult concepts using ideas they can relate to. There's nothing more satisfying than to witness a learner having an aha moment where they understand something new. I'm really excited about this program. I believe Microsoft has some of the most powerful and exciting software development tools available, and I can't wait for you to learn about them. I'm confident you'll have many of the aha moments as you gain new skills and reinforce existing ones. The learning experience in this course is designed to give you a comprehensive understanding of key concepts through various learning methods. You'll be guided through interactive, engaging materials that help you build practical and theoretical knowledge. Whether you're interested in front-end, back-end, or full-stack development, this program has the tools to support your growth every step of the way. Throughout the course, you'll be introduced to core concepts and key ideas in videos. These videos are designed to help you understand definitions, processes, and essential steps clearly and concisely. You'll get to absorb foundational knowledge, setting the stage for deeper exploration as you move forward. And when you need step-by-step guidance, screencasts will provide you with a detailed practical view. These screencasts will show you exactly what's on the screen and how to work through specific coding tasks. The course also includes readings that reinforce the key ideas presented in the videos. These readings are more than just supplementary material. They're job aids. You can print them out and use them as a reference while working on assignments or activities, helping to apply what you've learned in real-world situations more easily. Small activities are included to help you check your understanding of key ideas. These activities provide quick, interactive opportunities to practice what you've just learned. After completing each activity, you can compare your work with a fully explained example and answer key. This ensures that you always know if your answer is correct. Practical experience doing tasks you would in a job within this field is essential, and that's where guided labs come in. These labs take you through the implementation of different concepts step by step. As you work, you'll receive feedback and helpful hints, ensuring you can get the help you need when you need it. It's the perfect opportunity to practice in a controlled environment while learning by doing. After completing the guided labs, you'll move on to independent projects, or you try it. This is where you'll put your skills to the test, applying what you've learned in the labs. You'll work through real-world problems, cementing your understanding of the course material. The course will culminate in a practical project leveraging Microsoft Copilot that you can use as a portfolio artifact when you begin your job search in this field. As you progress through the program, the portfolio pieces will become stronger and better representations of the authentic experience you've gained. They'll showcase your understanding of code and the ability to implement different concepts from the developer program. This course guides you step by step from understanding concepts through videos and readings to apply them in activities, screencasts, and labs. Each part of the course builds on the last, helping you gain knowledge and authentic experience. By the end, you'll have completed real projects that not only showcase your skills, but can also be included in your portfolio as you start your career. Everything you do here will prepare you for success as a developer. Let's get started.
Throughout this course, you'll complete several guided labs. These labs are meant to give you an opportunity to practice your newly learned skills in an environment where you can get help and feedback as you complete coding challenges. This video will describe how to complete the guided labs in this course. We will explore a guided lab together so that you'll know what to expect when you come to one later in the course. First, let's check the content leading up to a guided lab. This structured content ensures that you have exactly the skills you need to complete the task. In this instance, there is a practical application video that describes in detail how this concept is used in real-world situations. Following this practical application video, you can review a reading that explains the concept in detail so you can go through this content at your own pace. Next, you'll find a video that works through the guided lab itself. This video won't give you all the answers to the guided lab, but it will provide an overview of the upcoming questions and challenges. Lastly, we come to the guided lab itself. The guided lab is a simulated code environment where you can experiment with code and receive hints and feedback in a realistic coding situation. To start, I'll click Start. In this lab, step 1 is an introduction to if-else statements, so I'll click Begin. Below the simulated code environment, I can find the specific instructions for this lab. Declare the variable age as type int. Place your cursor into line 2, type your answer, and select Enter to check your work. Alright, I think I know this one. I'm going to type in INT and hit Enter. Great, I got that correct, and I got a bit of feedback about my correct answer. To move on, I click Continue. And these instructions say, prompt the user to enter their age, place your cursor into line 4, type your answer, and select Enter to check your work. This one is a little trickier. Let me try type your age. Got it. This feedback for my wrong answer points me in the right direction. Let's try that again. I'm going to erase what I had here and then enter your age. Perfect. I'll click Continue. Let's try one more. Convert the input to an integer using int.parse and store it in the age variable. Place your cursor into line 6, type your answer, and select Enter to check your work. I'm not totally sure here, so I'm going to click on Hint and get some help. And the hint says use console.readline, and then an open and close parentheses, display a message asking their user for their age. Great, that helps. I'm going to click Continue and type in console.readline, and I've got it. That's how you work through a guided lab. Some questions will require more complex code to complete, so make sure you're using the hint function when you need it and reviewing the feedback provided for your right and wrong answers. Have fun completing these coding challenges that put your new skills to work.
In today's rapidly evolving tech landscape, artificial intelligence plays a key role in making development more efficient and intelligent. That's where Microsoft Copilot comes in. Microsoft Copilot is a powerful AI-driven tool that can assist developers in writing, optimizing, and debugging code. In this course, you'll leverage Copilot as a thought partner and a code-generating assistant, helping you solve problems, generate code snippets, and enhance your projects. The goal is to provide you with hands-on experience using a tool that real-world developers use to improve their workflow. In the last module of this course, you'll engage in videos, screencasts, guided labs, and independent projects that integrate Copilot. These labs will take you through how to use specific prompts to generate code, optimize solutions, and solve problems. You'll be shown step by step how to leverage Copilot's capabilities to strategically approach the final project. During the guided labs, you'll get hands-on experience working with Copilot. These labs are structured to show you how to craft effective prompts and work with Copilot's code generation features. You'll use it to assist in writing code, refining your solutions, and debugging. This practice will prepare you for the independent work you'll do in the final project. After the videos, screencasts, or guided labs, you'll move on to independent activities where you'll take control. Here you'll use Copilot to assist with various aspects of the project. You'll be making strategic decisions, but Copilot will support you by generating code, suggesting optimizations, and helping you troubleshoot. This prepares you to work more independently while still having the power of AI to assist. The final project will combine everything you've learned in the course, and you'll have Copilot as a key tool in your development toolkit. You'll use Copilot to help you generate and refine code as you combine the concepts from earlier lessons. The project is a portfolio-ready artifact showcasing your coding skills and your ability to leverage AI in modern development workflows. To succeed in the final module, actively engage with the guided labs and practice using Microsoft Copilot effectively. The videos and prompts will take you through Copilot and equip you to apply it strategically and independently. By the end of the course, you'll be fully prepared to complete the final project and demonstrate your skills using traditional coding and AI-assisted workflows. Welcome to the course. In this video, we will discuss how you can make the most of each part of the course to set yourself up for success. Whether you watch the videos, complete activities, or work through hands-on labs, each element has been designed to help you master the skills you need to become a confident and capable developer. The first step in every lesson is the videos. You'll be introduced to new concepts, definitions, and key ideas. Watch these carefully and take notes on the important points. The videos provide the foundational knowledge you'll need to build on, so don't skip them. They'll give you the context to understand everything that comes next. After each video, complete the readings. These readings reinforce the key ideas you've just learned and can serve as job aids. I recommend printing out the readings or saving them for quick reference. They'll be extremely helpful when completing activities, working on projects, or just needing a refresher. They're not just supplementary. They help you apply what you've learned to real-world tasks. Throughout the course, you'll find small but impactful activities. These quick exercises allow you to check your understanding of key ideas. Don't rush through them. Take the time to work through these activities thoughtfully. After each, compare answers with the answer key to check how well you understand the material. This is your chance to practice without pressure. At the end of each lesson, you'll encounter practice quizzes. These quizzes are a great way to ensure you fully grasp the concepts from the videos and the readings. Use these as a checkpoint to assess how well you retain the information. If you find yourself struggling, review the videos and readings again. The goal is to build confidence and solidify your understanding before moving forward. When you need to see the material in action, screencasts guide you. These videos show you exactly how to work through certain tasks step by step. If you ever feel stuck or unsure about applying a concept, watch the screencasts and follow along. This hands-on guidance is invaluable for understanding how the code works in real time and applying what you've learned. At the end of each module, there will be graded quizzes. These are an important part of your success as they allow you to demonstrate mastery of the material. These quizzes build on the practice quizzes, and they're a great way to ensure you're ready to move on to more advanced concepts. Treat these quizzes as milestones. Passing them means you're fully prepared for the next challenge. The guided labs are where you'll take the concepts from the lessons and apply them in a controlled, hands-on environment. These labs will take you step by step through tasks, including helpful feedback and hints. The more effort you put into the labs, the more you'll get out of them. It's all about learning by doing, so take your time and ensure you understand each step before moving on. After you've completed the guided labs, it's time to test your skills with independent projects or you try it. This is where you'll apply everything you've learned without step-by-step instructions. These projects are a great way to gauge how far you've come and to put your knowledge to the test. Don't worry if you feel challenged, that's part of the learning process. By completing these projects, you'll reinforce your skills and build confidence. Finally, at the end of the course, you'll complete a culminating hands-on project that you can use as a portfolio artifact. This project will showcase the skills you've gained throughout the course and give you something tangible to present to potential employers. As you progress through the program, these portfolio pieces will become stronger representations of your hands-on experience and understanding of key concepts. Success in this course comes down to using all the tools available. Watch the videos carefully, engage with the readings, complete the activities and quizzes thoughtfully, and take full advantage of the screencasts, labs, and projects. Each element of this course is designed to help you master the material step by step. By the end, you'll have a solid understanding of the concepts and real projects to prove your skills. Remember to persist, take your time, and you'll be ready for a successful career in development. Developing a functional library management system takes careful planning and step-by-step execution. With Microsoft Copilot's assistance, you'll work on a project to build, debug, and optimize a system that allows users to manage a library of books. In this video, we will explain the end of course project. This project simulates real-world software development. You'll start by building the basic features of a library management system, then debug and refine your code as it becomes more complex. By the end, you'll integrate everything into a fully functional and optimized product. The goal is to experience the complete coding process, writing, debugging, and improving your code. First, we will write the core features of our library management system using Microsoft Copilot. This includes adding new books, removing books, and displaying the current list of books using control structures and loops. This step establishes the basic functionality that will be expanded later. Once the core features are in place, errors will arise as you handle book inputs and removal. In this step, we will focus on debugging using Microsoft Copilot. Copilot helps identify and suggest fixes for common issues, like trying to remove a non-existent book or dealing with a full library. Debugging at this stage ensures the system works correctly. After debugging, we'll use Microsoft Copilot to improve the quality and efficiency of our code. This step includes simplifying repetitive tasks, optimizing loops, and improving readability. Copilot will assist in refactoring the code, suggesting best practices to reduce complexity and enhance maintainability. Finally, we'll practice solving advanced coding challenges with Microsoft Copilot. You'll be tasked with extending the system, like adding a search feature for books or limiting how many books a user can borrow. Copilot will help you efficiently solve these challenges and integrate them into your project. This project guides you through the complete coding process, from writing the initial code to debugging to optimizing and solving new challenges using Microsoft Copilot. By following this structured approach, you will create a polished library management system that mirrors real-world development workflows.
Welcome to Foundations of .NET Development and Visual Studio Code Integration. In this module, you'll dive into the essentials of .NET, harness the power of Visual Studio Code, and master setting up and managing your projects. Get ready to elevate your front-end and back-end development skills with these powerful tools. We will start by exploring front-end and back-end development in .NET environments, focusing on its role in building robust, scalable applications and enhancing developer efficiency. Next, we'll explore how Visual Studio Code integrates with .NET projects, enhancing your development workflow. Then, we'll examine how to set up your .NET development environment, ensuring everything is in place to start coding. After that, we'll identify the key steps for initiating a new .NET project, from planning to execution. Finally, we'll explore best practices for organizing your .NET projects, focusing on effective file structure and code management. By the end of this module, you'll have the skills and confidence to develop and manage front-end and back-end projects in .NET using Visual Studio Code. Let's get started with Foundations of .NET Development and Visual Studio Code Integration. Have you ever wondered how the apps and websites we use every day come together to create such seamless experiences? There's a whole world behind every button you press and every web page you scroll through. This world is divided into two main areas: front-end and back-end development, each with its own set of responsibilities and challenges. In this video, we will describe front-end and back-end development. Front-end development is the practice of building the visual and interactive elements of a website or web application that users directly interact with. Front-end development is all about what you see and interact with on a website or app. This includes the layout, buttons, text, and even animations. Front-end developers use a combination of HTML, CSS, and JavaScript to make sure everything looks good and works well. Now that we know what front-end development is, let's explore the types of tasks front-end developers handle in their daily work. First, front-end developers structure content with HTML, style it with CSS, and make it interactive with JavaScript. For example, they might build a responsive menu or create a form that checks your information before submitting it. Second, front-end developers often use frameworks like React or Angular to speed up their work. These tools help them build complex features like a search bar or a user profile without starting from scratch. Third, they ensure that websites work across all devices. They adjust layouts, fonts, and images so everything looks great on screens of all sizes, whether it's a phone or a desktop. Fourth, they focus on optimizing the performance of websites by minimizing load times. They compress images and streamline code so users don't have to wait for pages to load. Fifth, front-end developers work with designers to improve user experience. They ensure that navigating the website is intuitive and simple, such as making a checkout process faster or improving layout for better browsing. By handling these tasks, front-end developers create a seamless and visually engaging experience for users, ensuring the website is easy to navigate and responsive across all devices. Now that we've covered front-end development, let's shift to what back-end developers do behind the scenes to ensure the front end runs smoothly. Back-end development is the practice of building and managing the systems that power apps and websites, such as data processing, storage, and application logic. Back-end development is responsible for the servers, database, and logic that make a website function. Back-end developers ensure that all the data the front end needs is processed securely and efficiently. With a clear understanding of what back-end development involves, let's explore the daily tasks that back-end developers perform. First, back-end developers write the code that processes requests, such as logging in or submitting forms. They use server-side languages like Python, Ruby, or Node.js to ensure everything on the server works correctly. Second, they manage databases, which store all the website's data. They write queries to retrieve or update data, such as fetching a user's profile when they log in. Third, they ensure that the system is secure and scalable. This involves protecting sensitive information and designing systems that can handle more users as the site grows. Fourth, backend developers use frameworks like Django, Express, or Spring to streamline server-side tasks. These tools help them manage things like login systems and data storage efficiently. Together, these backend tasks ensure that the website's data flows smoothly and securely, providing the necessary support for everything the front end delivers to the user. Front-end and back-end development work hand in hand to create a seamless web experience, whether you're seeing a smooth interface or accessing data in the background. Both roles are essential to building the websites and apps that we use every day. Starting a new project from scratch can be overwhelming, much like a chef trying to grow their own ingredients before cooking. Instead of reinventing the wheel, developers can use platforms like .NET, which offer pre-built tools and libraries. This allows you to focus on what truly matters, bringing your unique ideas to life efficiently. Development platforms provide sets of tools that work together like a house kit, allowing you to focus on the unique aspects of your application. In this video, we will learn about the .NET ecosystem, including its significance and different versions. .NET is a platform created by Microsoft that simplifies the software development process by providing a unified set of tools and pre-made code. Originally launched as the .NET Framework, it aimed to address challenges such as using multiple programming languages and managing complex dependencies on Microsoft Windows operating system. The .NET platform offers a wide range of features, making it a versatile choice for various development projects. Initially, it was exclusively used for Windows-based applications, but with the advent of .NET Core and later .NET 5, it became cross-platform, meaning it works on different operating systems. This means developers can now build and deploy applications on Windows, Linux, and Mac OS. .NET's ability to work across different operating systems has made it a preferred choice for developing a wide range of applications, including web, desktop, mobile, cloud, and Internet of Things applications. One of the key features of .NET is its support for multiple programming languages, including C#, F#, and Visual Basic. This flexibility allows developers to choose the best language for their specific tasks. Additionally, .NET includes a comprehensive collection of reusable code and tools, known as the Framework Class Library, which provides functionalities for data access, security, web development, and more. The flexible design of .NET allows developers to include only the parts they need, leading to improved performance and efficiency. .NET also excels in web development through ASP.NET Core, a powerful framework for building modern web applications. ASP.NET Core is known for its high performance and ability to handle a lot of traffic, making it ideal for applications hosted on the internet and those that use small independent services. Furthermore, with the introduction of Blazor, .NET can take advantage of a technology called WebAssembly to run .NET code in a web browser, overcoming a previous limitation of every programming language except JavaScript. Despite its widespread use and robust feature set, .NET often faces misconceptions that can deter potential users. One common misunderstanding is that .NET is only suitable for Windows development, which stems from its early days as a Windows-centric framework. As mentioned previously, with the introduction of .NET Core and now .NET 5 and beyond, the platform has become fully cross-platform, supporting development on Windows, Linux, and Macs. Another misconception is that .NET is outdated and not suitable for modern applications. And this couldn't be farther from the truth, as .NET has evolved significantly, embracing open source principles and modern development practices, including cloud-focused development, small, independent services, and software packaging methods. Finally, some believe .NET is a closed-source ecosystem controlled solely by Microsoft. While Microsoft remains a key contributor, the platform has been open source for years, encouraging community contributions and transparency. It's an inviting and versatile platform for developers of all backgrounds, offering a wide range of tools and libraries for various development needs. In conclusion, the .NET platform offers a comprehensive solution for modern software development, whether building web applications, mobile apps, or complex enterprise systems. .NET provides the tools and frameworks necessary to succeed in today's competitive technology landscape. VS Code is an incredibly powerful code editor. It is lightweight yet robust, making it an ideal choice for developers at all levels. Let's delve into some of the key features that make VS Code stand out. Above all, VS Code is flexible and customizable, which allows it to be both lightweight and robust. When you first install VS Code, it has some basic tools for writing code. You can then install additional tools that are tailor-made for the programming languages and workflows that you use. You can also customize your editor itself to fit your style and needs. In this video, we will explore the high-level features of Visual Studio Code. Understanding these features will give you a solid foundation to see how this tool can enhance your development process. Let's dive into one of these powerful tools, the built-in terminal. VS Code has a built-in terminal, so you don't have to switch to other windows to run commands or scripts. You can do it all right inside VS Code. It's especially handy for tasks like building your project, managing your code changes, and running other commands directly from within your coding workspace. Another critical feature of VS Code is its use of modular extensions. Extensions are add-ons that enhance the functionality of the editor. Tools are added to VS Code as extensions. The primary way to get extensions is through the built-in extension marketplace, which is like an app store for coding tools. For example, some extensions can check your code for mistakes, give you shortcuts for common coding tasks, or connect with other services you might use. For .NET developers, there are special extensions that add even more helpful features, making it easier and faster to write and manage your code. Let's explore the C# DevKit extension in a bit more depth. It is a particularly beneficial tool for .NET developers. It includes the C# extension and the .NET install tools, which form a powerful combination. First, let's discuss the C# extension, which powers IntelliSense, debugging, and project management for .NET applications. Think of IntelliSense as a helper that understands the code that you're writing. As you type, it suggests what you might want to write next based on what you've already typed and the rules of the programming language, in this case C#. This is known as code completion. It means you don't have to remember everything yourself. It helps you write code more quickly and with fewer mistakes. You can take code completion a step further using Copilot, an AI-powered tool that helps you write code faster and more efficiently. It acts like a smart assistant, providing suggestions and code completions as you type. Copilot can generate whole blocks of code based on the context of what you're working on, making it easier to tackle complex problems or repetitive tasks. VS Code is also great for debugging, which is finding and fixing mistakes in your code. You can mark specific spots in your code where you want to pause and check what's happening, which is called setting breakpoints. Then you can step through your code one line at a time to see exactly how it runs. You can also look at the values during different parts of your code execution to make sure everything is working correctly. The .NET Install tool is used to manage installations of the .NET SDK, which you need to build and run applications using .NET. It includes everything required to develop software, such as the .NET Runtime, which allows your application to run, and the .NET libraries, which provide pre-written code to help you with common tasks. Additionally, it comes with a .NET CLI, which is a command line interface that lets you create, build, and manage your projects using simple commands that you write in a special tool known as a terminal. It's also worth noting that Microsoft has a special piece of software called Visual Studio as opposed to Visual Studio Code. Visual Studio is a much larger piece of software with virtually every feature you would need to be a productive developer baked into the editor. We're focusing on Visual Studio Code in this course because it tends to be more approachable for new developers and you can easily install it on any operating system. If you work on a large code base, especially in an enterprise environment, there's a good chance you might want to work with Visual Studio. But just know that with the use of extensions, Visual Studio Code can do virtually anything that Visual Studio can. In this lesson, we explored how Visual Studio Code is a powerful, lightweight, and customizable tool that meets the needs of developers at every level. Its built-in features, like the terminal, code completion, and debugging, paired with a vast extension marketplace, make it incredibly versatile. Whether you're working on a small project or managing large-scale applications, VS Code provides the flexibility and tools to enhance your productivity and help you create high-quality code efficiently. In today's video, we will walk through the process of installing the .NET SDK. Installing the .NET SDK will allow us to run .NET code, use .NET libraries, and explore the .NET command line tool. We will walk through installation of Windows, but the process on Mac is quite similar. Same for Linux. In this video, we will explore how to install the .NET SDK. The first thing you will want to do is download the appropriate installer for your operating system. You can find the installer at https://.net.microsoft.com/download. It should automatically detect your operating system, and you should see the correct installer listed here. In this case, it's the ARM64 installer, which is what I need. But if you need a different installer, you can click this link right here, the all.NET 8.0 downloads, and this will give you other options. I will go ahead and click this to start installing it. And this should download. And you can see here, I had downloaded this previously. But we'll go ahead and open up that file. And if you don't have it open here, you can navigate to where you downloaded that in your file system and open it from there. So we're going to go ahead and click install. And you're going to want to say yes to allow it to make changes to your device. And you are just going to wait for this to do its thing. It'll take a few minutes sometimes, depending on how fast your computer is. Now that that has installed, you should see this list of resources. You can look here for the .NET documentation, the SDK documentation, release notes, tutorials. If any of that excites you, you can go ahead and click those notes, but we will be covering most of this material in the course, so you can just go ahead and keep listening. So we'll go ahead and click close here. And the next thing you're going to want to do is check to make sure that .NET installed. So you're going to want to open a terminal application. Now, just about every operating system has a terminal now. For a long time, Windows just had PowerShell, but now you can access, you see here, PowerShell through Windows Terminal. So Mac has a terminal, Windows has a terminal, Linux all have a terminal. So all a terminal is a special piece of software that allows you to interface with your computer and run different applications by using text codes. And so in this case, you can type into this prompt here, and you should see this sort of flashing indicator here. If you don't, it means you're not actually in. You can see here I just clicked out and I'm not clicked in. So if I type, nothing will happen. But now if I click back in, there's that indicator again. And all you're going to do is type one word, no capitalization, .net, .net. Anything different than that, and this will not work correctly. Then hit enter, and you should see this usage message. So this is telling you how to use the command. You would not see this if you actually didn't have it installed. If you didn't have it installed, you would see something like this. So I'm going to misspell the name, and it's going to say, that is not recognized as a commandlet, a function, a script file, or an operatable program. So that means that this is not actually a piece of software that's installed. So if you typed in .NET and you saw a message like this, something went wrong. And what you're going to want to do is go ahead and restart your terminal and then try running the command again. And if that doesn't work, go ahead and restart your computer. And if that doesn't work, go ahead and retry this installation process one more time. Now that you have the .NET SDK installed, we can go ahead and install Visual Studio Code. So I have another tab here open, and what you're going to want to do is navigate to this URL. This is code.visualstudio.com/download, and then click on the correct installer for your system. In this case, I'm looking for Windows 11. It looks like this will work on the x64 and the ARM64, which is what I am working on. So you can go ahead and click that, and it will start you here with your download. You will click that download once again, and this time around, you're going to want to accept the agreement. Going to click next here if you like the location. If you don't, you can move it somewhere else, but I find the defaults tend to be really good, especially if you get lost, because it will be in a place that the internet knows about. So let's go ahead and check these next options here. Now the first two options I wouldn't worry about, but these last two you definitely want to leave clicked. So this first one, register code, is an editor for supported file types. This means that Visual Studio Code will be able to open different programming types of file directly from that file. So it's like if you have a spreadsheet, it will open directly into Sheets or into Microsoft Excel. So if you try to open a code file, it will open directly in Visual Studio Code. You can also add to path, and this is important. So this will allow you to run Visual Studio Code from the terminal like we just showed, sort of like .NET. You don't need to do this, but I highly recommend it. It's really handy to have around. So with those two, we will go ahead and click Next and install. Once this is finished installing, you can go ahead and launch Visual Studio Code by just leaving this checked, but I'm going to go ahead and close that so I can show you how to get to Visual Studio Code if you haven't already opened it up. So I will go ahead and type in Visual Studio Code, and that will bring up the best match here is Visual Studio Code. Now both Linux and Mac have sort of search options similar to this. You can also type in VS Code. That tends to work on most operating systems. And now that we're opening here, you can see this is Visual Studio Code. So you have now installed Visual Studio Code and the .NET SDK, and those are the first two critical steps in starting to work as a .NET developer. Now that you have Visual Studio Code installed, let's go ahead and configure the working environment. In this video, we will learn how to configure the .NET development environment. When you install Visual Studio Code, you'll see a window like this. And so there's some resources here on the right for getting started. I highly recommend clicking these Learn the Fundamentals or Getting Started with VS Code. And this will give you a handy list of things that you can customize. But first, let's discuss how to navigate in Visual Studio Code. You'll see your main working area here with tabs, sort of like a web browser, where you can close these, move these, and even do a split pane where you have them side by side. Then at the top here, you have a navigation bar that allows you to do things like save files, change your selection, work with the terminal, and run your code. Over here on the left, you have the File Explorer in this sidebar menu. You also have Search, Source Control. You can run and debug your code. And notice you have Run and Debug down here, and you also have Run and Debug up here. Additionally, you'll also see hotkeys next to nearly everything. So there are multiple ways to get to what you're trying to get to through different menus or hotkeys. I highly recommend taking a minute to learn a few hotkeys for skills that you're using constantly. Don't try to learn every hotkey in the editor. There are many of them, but there are some hotkeys for navigation, for searching for files, for opening new files, and formatting your code that I find myself using constantly. As you find yourself doing something repeatedly, go ahead and see if there's a hotkey that you can use for that. Now that we've covered the basics of navigation, let's explore how you can personalize your environment. Visual Studio Code is highly configurable.
You can make endless changes to your development experience, and you will surely continue fine-tuning your editor experience to meet your needs. That said, I recommend you stick with the default settings for most things. Heavily customizing your editor can slow down performance and make it harder to solve any issues you run into with a quick web search. But you can do things like change your theme, add support for different languages, which we will do. You can fine-tune other settings, you can sync across different devices, and you can use the command palette. The command palette is one of the best ways to navigate around Visual Studio Code. And if you click this option here, you can see unlock productivity with the command palette. And there's a very important hotkey here. So if I hit Control, Shift, and P, it will open up this little prompt. Now this is going to look a lot like a terminal, and that's because it works similarly. I can type in a particular option I want to use, and this is a command I can run. I can close window. I could call this directly with a hotkey, but if you don't know how to do something, you have this huge list of commands that you can quickly search for the way to do something. And it is an absolutely huge list of commands. And as you add more extensions, you can add additional commands into this list. The next thing we want to do is install some extensions, and you can see here you can do this from the command palette, but I want to show you how to do it through the menus. So over here on the left side is the extensions button, and you're going to click that, and this is where you will install and manage extensions. Perhaps the most important extension to add is the C# Dev Kit for working with .NET. Now I can see it right here, but if you don't see it at the top of this list, you can type in C# Dev Kit, and that will do a quick search for it. And you can click install directly here, or you can also click on this listing to see all of the information about this extension. So you can see a C# Dev Kit, who made it, how many times it's been downloaded, how many stars does it have, and you can also see more information along here. This is really handy, especially once you've installed it, because it'll tell you the types of things you can do. So I'm going to go ahead and click install here, and you'll see this go a little bit darker. And we're going to wait a second for this to install. And once that extension is installed, you should see this installed check mark, and you should see the disable and uninstall buttons. If you ever wanted to remove the extension, you would use these, or if you want to disable it, you can use this. You may also find a time when the extension is having troubles and not working appropriately. There will be an option in here to restart that extension. And with that, congratulations! You now have all the basic tools you need to be a .NET developer. You have the .NET SDK, you have the C# Dev Kit installed in Visual Studio Code, and you are ready to rock. As you move through your journey as a developer, you may want to add additional extensions, but this simple setup provides the backbone for millions of .NET developers around the world. In the past, project creation could be a real pain. You have to make multiple files in the right directories and put the same boilerplate information into every file. Luckily, modern dev tools have made it much easier to create new projects, and .NET is no exception. Using the .NET CLI or the command palette in VS Code, you can quickly set up basic .NET projects that you can customize to meet your needs. In this video, we will build an understanding of the initial steps to create a new .NET project. We will walk through the process of creating a project using Visual Studio Code. If you are already familiar with using the command line, you can also create projects using the .NET New command. Let's begin by creating a new project. To create a new project, you can do it through this button here in the File Explorer if you have the C# Dev Kit extension installed, but I prefer to do it through the command palette. The key code there is Control-Shift-P, that's the hotkey, and you can type in .NET New Project, and that will show you an option here for this command. So if you click .NET New Project, you'll see here a list of the different types of projects you can create. Now there's a whole long list of these here, and so the main ones you're going to be interested in for doing web development are these ASP.NET Core ones and the Blazor ones, but there are a bunch of different types of projects. We're not ready for web development yet, so we're going to create a console app, and so this is an application that will work in the terminal. So I will click Console App, and then I will select a folder where I want to put that. I will put it in my Documents, and I will call this project Console App. Hit Enter. This will have a default folder that will be created here for Console App. You could put this anywhere you want to, but I find having it in a folder named the same thing is quite useful. This will go ahead and create a bunch of folders and files. Now you're going to want to trust the author of these files or folders. So this is your computer programmatically building these files. So I'm going to say, yes, I trust the authors. And that will allow me to access these files. So these have now been created by .NET. If you don't see the folders over here, click into the File Explorer. You might be in one of these different menus. As I mentioned earlier, we create several files here. A lot of these are really complicated and would take you a long time to build manually. But at the heart of them is this program.cs file. This is where you will write your custom code. You can see here we have a single line of code. It's console.writeline hello world. This line of code calls the console.writeline function, which is a special function that writes a new line of text in the terminal. In this case, it's taking a single argument, which is the text that should be shown. In this case, hello world with an exclamation point. Because this is a terminal app, it makes sense to run this using our terminal. So we can use the .NET CLI to run our program, and all we have to do is type .NET run followed by the name of our program. In this case, we'll type /program.cs. A handy trick here is if you type in .NET run, then the letter PR, and then hit tab, it will automatically fill. And that makes it much easier. So again, you can type /program.cs or type /PR tab, and it will auto-complete that for you. And we can go ahead and run that program. And if this is the first time you've run that, it's going to take a second because it's actually building the code that will run that function. Remember, C# is a compiled language. The result of this program is you should see hello world in the terminal output. You can see it right here. So this is a text that is actually created by our code. We can go ahead and make it something different. So let's make that say hello.net. And I will make sure to go ahead and save that. If you don't, you won't see the changes. I'm using the Command S hotkey there. And let's run that one more time. And this time you see hello.net. By following these steps, you've officially written your first .NET code. This is an important milestone as you continue your journey towards becoming a developer. Well done. Imagine you've just laid the foundation for a new building. Before adding walls and windows, you need to ensure the blueprints align perfectly with your vision. In the same way, configuring the initial settings is a crucial step when starting a new .NET project to ensure everything runs smoothly. In this video, we will configure initial project settings. The first place we will search is our csproj file. The name of the file will match the name you specified when you built the project. This is a special file that defines how your project should handle running, testing, building, and other types of configuration. We have a relatively basic setup here, so this is quite simple. You may see much more complicated csproj files in the future. The data in a csproj file uses XML, a format for organizing and storing data in a text format that is both human readable and machine readable. The text between angle brackets is called a tag. Tags come in pairs, an opening tag and a closing tag. The closing tag begins with a backslash. Some information goes between the tags. You can see here you can nest tags in other tags. This output type tag has a value inside that is just simply text, in this case, exe. Tags can also have parameters. The first tag we encounter here is the project tag with the attribute SDK equals Microsoft.NET SDK. So this is what's setting metadata. So this isn't actually the data that's held inside the tags. This is sort of data about that data. So this is another way that you can encode information in XML. You can put values between the tags. You can have these attributes that live within the tag itself. This tells a tool called MS Build what kind of project you're working on. If this is a web project, you might find .sdk.web instead of just .sdk. Or if it was a desktop application, you might find sdk.windows desktop. Another important piece of information is the target framework, which in this case is .NET 8.0, which means this uses .NET version 8, which is the latest stable version as of the recording of this video. If you wanted to use a different version of .NET, this is where that would be specified. In the future, it will likely be .NET 9 and beyond. Using a tool like C# DevKit to scaffold out these files has given us a great starting point. You often won't need to worry about modifying your CS proj file. It's useful to know what's in here, but don't worry too much about knowing exactly what all of these things do. If you ever need to find something specific, you can research it later. So that is the first place where you will see configuration in a .NET project. Next, we might want to add packages. Packages are pre-written code that you can utilize in your project. Packages in .NET ecosystem are added by a piece of software called NuGet. So if we look here in our program CS file, you'll see that we have a relatively basic console app. It just has this single console.writeline with hello world. I like what we have so far, but I'd like to change the color of the output text. To accomplish that, let's use a package called Pastel. If we open up the command palette, let's see if we can find a way to add a NuGet package. NuGet is spelled N-U-G-E-T, so let's type add NuGet to see what's here. Hey, there's the command we want right there. NuGet add NuGet package. The package was called Pastel, so let's type that into this search bar and hit enter, and it will run a search for Pastel. And here is the first one we want, this Pastel option right at the top of the list of returned packages. Next, it will ask us to select the version. At this point, 5.1.0 is the latest, but if you want a different version, or if in the future there's a newer version, you can go ahead and select that. If you're following along with this code, it's best to use the exact same version in case the code changes. Now, if we go over to our CS proj file, you should see something new. This item group with package reference include Pastel version 5.1.0. This is showing us that we have installed the Pastel package and that is a dependency of this project. So that means that is a piece of code that our code is now going to rely on. First, we'll go into our program.cs file and select just after the closing double quotes. I'll type in period, then capital PAS, and you can see here it's starting to autocomplete to Pastel. So I'm going to go ahead and click that, and I could just type this in, but if I click here, it's going to do something really useful. If I click that, you'll see it added this using Pastel. This is going to provide us with the import for this package. That means that our code now understands where Pastel is coming from. It's coming from an external package or library. Next, let's open up some parentheses. And if I type in color dot green and mind the capitalization here, you need a capital C with color and a capital G with green, or this code won't work correctly. Again, we can use IntelliSense here. It's showing us all of the different options for colors that start with green or have green in their name. In this case, I'm going to choose light green, but you can choose any color you like. Again, make sure to use capitalization, otherwise this code will not work correctly. Now, if I save my file and open up a terminal again, now if I type .NET run and then add my program file to the end of that, so .NET run period /program.cs and hit enter, you should see the output here, which is hello world now in light green instead of that light gray color. Excellent. Our project is really coming along, thanks to our knowledge of the CS proj file and adding an external package like Pastel. Imagine you've just finished coding your first .NET application. What's next? How do you ensure it's ready to run and distribute? Let's discuss what happens when we run and build our code. In this video, we will run a new .NET project. We showed how to run our application using the terminal, which makes sense because it's a terminal application. But what if we wanted to make a different type of application, like a web application or Windows application? You can still run them from the terminal, but there's also a handy feature built into VS Code that will let you run your application through the graphical user interface. You can see here that we can click Run on the left side of the screen, and that will allow us to run and debug our code. So if I click Run here, I can go Run and Debug. It'll ask us what language, and in this case I'm going to say C#, and the C# console app, this will be my launch configuration, and now our application is running. Now this will take a little bit the first time you start this application. Because this is a terminal app, it automatically opens the terminal, and here is our output. You see the hello world. Let's talk briefly about what happened behind the scenes when we ran our code. C# is a compiled language, meaning that the code that we write needs to be converted into instructions that a computer can execute before it can be run. This conversion process is often referred to as building the application. When we use the .NET run command, it compiles or builds the application first and then runs it. That's what's happening behind the scenes when we use the graphic user interface to run our code. After the application is built, the compiled output is placed in the bin folder. So if we go back to the File Explorer and look at bin, you'll see this is now full of files. This is the code that was run to create this terminal output. Typically, you will just want to run your application, but sometimes you may want to build it without running it. To do this, we can use the command palette again, and we can type in build, and you should see an option something like this where it says .NET:build. That's what we're looking for. That is the build command. And if we hit build, it will once again go through that same process, but this time we won't see that same terminal output. And that's because our code is built, but not run. We could also accomplish the same thing by opening up a new terminal and running .NET build. This will run the same command. And you can see here that we have now built our project once again. Not only can we build our project, but we can also remove it. If you ever want to remove your compiled code, you can use the .NET clean command. You could also do this from the command palette, but in this case, we'll go ahead and use the command line. And there we go. You have seen we now have an empty folder up here. That's because all of our binaries have been removed. It does leave some of the temporary files in OBJ, but our binary outputs are now clean. You would want to clean your code if you accidentally created files that wouldn't run. Or maybe you have some outdated code that you don't want hanging around. Sometimes your cache gets corrupted. And don't worry that you will lose your code when running .NET Clean. It only affects the bin folder and not your C# files. You've successfully run, built, and cleaned your first .NET application. Understanding how .NET handles code execution and project management is essential for ensuring your application is ready for further development and eventual distribution.
Welcome to Applying Programming Foundations. This module will deepen your understanding of the fundamentals of programming concepts and help you integrate them effectively into your practical projects, building a strong base for more advanced development. To reinforce your foundational knowledge, we will begin by reviewing essential programming concepts, such as variables, data types, control structures, loops, methods, and pseudocode. Next, we will integrate logical thinking with these programming fundamentals, enhancing your problem-solving abilities. Then, we will introduce basic debugging techniques and tools equipping you with the skills to identify and fix errors in your code. After that, we will practice writing simple programs in C#, applying everything you've reviewed to build functional applications. And finally, you will create a project that combines all of these concepts and debugging techniques, giving you practical experience in applying your skills to a complete development task. By the end of this module, you'll have the confidence and skills to apply key programming concepts in practical projects and effectively debug and build applications in C#. Let's get started with applying programming foundations. Programming is like learning a new language, one that allows us to communicate with computers and bring our ideas to life. Just like any language, there are core elements that we must understand to express ourselves effectively. In programming, these core elements include variables, which store information, data types, which define the nature of that information, and control structures, which manage how that information is used. Mastering these fundamental concepts is essential. They form the foundation of everything you'll create as a developer. In this video, we will summarize key programming concepts. One of the most important concepts in programming, and the one that started it all, is Boolean variables. These variables allowed computer scientists to actually make computers think logically as humans do. In C#, A Boolean variable is a type of variable that can hold one of two values, true or false. These values are commonly used to represent binary states such as yes or no, on or off, true or false. There you have it, simple but fundamental and powerful. Imagine you're developing a video game and need to track whether a player is alive or not. A Boolean variable could indicate whether the player is alive. To do this, we write bool to indicate it is a Boolean variable, then isPlayerAlive, which is the variable's name. We assign the value of true using the equal sign and writing true. Boolean logic in programming uses true-false values to perform logical operations like and, or, and not, which are crucial for making decisions in your program. The following are the basic operations you can perform in Boolean logic. The AND operation returns true only if both conditions are true. The AND operation is a logical operation that evaluates multiple conditions. It will only return a result of true if every condition being checked is also true. If any one of these conditions is false, the result will be false. The AND operation is particularly useful when you need to verify multiple criteria meet at the same time. For example, if you want to ensure that a user is both logged in and has the appropriate permissions, you would use the AND operation to check both together. In the C# programming language, the AND operation is represented by two ampersands. When you use ampersand between two conditions in C#, it checks whether both conditions are true and only returns true if they are. For example, let's say that in our game, a player is ready when it is at full life and it is at full stamina. You'd use an AND operator, ampersand, between the two variables, is at full life and is at full stamina. The operation returns true only if both conditions are met. Let's say these are the bars of life and stamina of the player. Here, both bars are below full, so the operation to determine whether the player is ready returns false. Even if one of the bars goes up to the top at full, the players are still not ready. The operation keeps returning false because one of the variables is false. It is only when both conditions are met that we have a player that is ready to play. There's another Boolean operation that helps you calculate if at least one of the values is true. The OR operation is useful when determining if at least one of several criteria is satisfied. For example, if you want to allow access if a user is an admin or has a special pass, you would use the OR operation to check if at least one of these conditions is true. In the C# programming language, the OR operation is represented by the two vertical bars. When you use vertical bar between two conditions in C#, it checks whether at least one of them is true, and if so, returns true. While AND requires both conditions to be true, OR is more lenient, returning true if just one condition is met. Let's see how OR works. In our example video game, you might check if a player is defeated and thus not ready to fight by checking if he is either at 0 life or 0 stamina. This operation returns true if the player is 0 in life, stamina, or both. Let's say these are the player's life and stamina bars. Right now, they are both at 0, which means that the player is defeated, of course. But since this is an OR operation, the player is defeated if just one of the variables is true. Even when the player has some life, in this example, the player is still defeated because his stamina is at 0. It is only when both variables are false that the operation returns false. This is when the player has a little bit of both, life and stamina. In summary, AND and OR operations work on the values of two Boolean variables. If both variables are true, then both operations return true. However, if one variable is true and the other one is false, then AND will give you false, but OR will be more lenient and give you true. And finally, if both are false, then the result will be false for both operations. The NOT operation is a logical operation that flips or inverts the value of a Boolean. If the Boolean is true, applying the NOT operator will make it false. And if the Boolean is false, the NOT operator will make it true. The NOT operation is particularly useful for toggling states in programming. For instance, if you have a feature that needs to be turned on or off, the NOT operation can switch between the two states. If the feature is currently on, true, applying NOT will turn it to false, off, and vice versa. In C#, the NOT operation is represented by the symbol exclamation point. When you place exclamation point before a condition in C#, it inverts the condition's Boolean value. For example, if you have a condition is logged in that is true, then writing exclamation point is logged in will evaluate to false. As another example, in the video game, you might want to know whether the player is not defeated. In that case, you'd use the not operator exclamation point before is defeated variable. After understanding how to store and manipulate data with variables and Boolean logic, the next step is learning how to control the flow of your program. This is where control structures guide your program's decisions and actions. Conditional statements are like decision-making tools in programming, helping guide what a program does next based on specific conditions. For instance, think about the part of a game where there is a door and it only opens if the player has a key. But what if the player doesn't have the key? That's where an else statement comes in, offering an alternative action. If the player doesn't have the key, then perhaps the game displays a message saying the door is locked. And what if you have multiple options? What if the rules state that the player can use different potions? This is similar to a switch statement, which checks a variable against multiple values. A switch statement lets you choose different actions based on several predefined conditions. Loops are another essential concept in programming. They allow you to repeat a set of actions until conditions change. Imagine our hero needs to sell every item in his inventory. While we could go one by one on each and every item and sell each of them, it'd be more concise and computationally efficient to just write some code that repeats in a loop for every item the hero has. A for loop is ideal here, letting us iterate through each item individually. Similarly, if our hero must continue attacking enemies as long as they keep spawning, a while loop would be the right choice, allowing the code to run until no more enemies appear. This loop keeps running until the condition, like the spawning of new enemies, no longer holds. In this video, we have summarized key programming concepts. Understanding the fundamentals of programming such as variables, Boolean logic, conditional statements, and loops is crucial for any developer. These concepts are not just building blocks, they are the foundation upon which more complex programming skills are built. By mastering these essentials, you're preparing yourself to tackle more advanced challenges and create more sophisticated programs. Remember, like any new language, programming becomes easier with practice. So keep experimenting, keep coding, and soon these concepts will become second nature. Imagine trying to solve a complex problem without breaking it down into smaller, manageable steps. It would be overwhelming. In programming, pseudocode and methods help us do just that. Pseudocode is a powerful tool that helps us plan and think through our logic before we even start coding. On the other hand, methods allow us to organize our code into reusable blocks, making our programs more efficient and easier to understand. In this lesson, we'll explore how methods structure our code and how pseudocode serves as a blueprint for solving programming challenges. Pseudocode is a plain language description of the steps in an algorithm or code structure. Pseudocode serves as a bridge between your initial ideas and actual code, allowing you to outline the flow of your program in simple terms. When writing pseudocode, the key is keeping it straightforward, concentrating on the core logic rather than getting bogged down in details. Let's look at how to write pseudocode. To write effective pseudocode, keep it simple, focusing on the main logic. For example, if you were writing pseudocode for a method that accelerates a car, you would write initialize car, accelerate car, then in accelerate, you would write if gas is greater than 0, increase velocity by 1, you'd return the velocity, display an animation, and then it ends. Pseudocode allows programmers to focus on the logic without getting bogged down by syntax. While pseudocode helps you concentrate on the logic of your program without worrying about the syntax, methods bring that logic into action with your code. Methods are essential tools that allow you to organize and reuse your code efficiently, applying the logic you've planned out in your pseudocode directly to your program's functions. Methods are blocks of code designed to perform a specific task. Think about a method as one of your teammates in a significant event planning. They will have a set of responsibilities that they will enact once you give them a call. Methods help programmers break down complex problems into manageable pieces. For example, imagine we're building code for a car in a video game. In this scenario, you will use a method to accelerate the car by calling it. You would have to say accelerate and the car will do so. Declaring a method involves specifying its name, return type, and parameters. For example, this method, called accelerate, could be used to accelerate a car in, let's say, a game or simulator. A method can have parameters to specify its intended behavior. For example, we added a gas parameter in our car video game, which tells the method how much to accelerate. Parameters allow methods to be flexible and reusable for different inputs. Methods must define a return type. Return types specify the type of value a method will return. This can be useful when you want the method to inform the caller about something. For example, if we want to know the car's final velocity, we can use an int return type, which will tell us the car's actual velocity after acceleration. To call a method, you call it with the appropriate arguments. In this example, we just use its name, accelerate, passing the appropriate arguments for how much gas we are inputting, 10 for this example. In this video, we've seen how methods and pseudocode work hand in hand to simplify complex programming tasks. Just like the method to accelerate a car in C#, methods in your code encapsulate functionalities, making your programs more organized and reusable. Pseudocode helps you plan these methods clearly, allowing you to focus on the logic before diving into the coding details. By mastering both, you can build more efficient, maintainable, and understandable programs, much like how clear instructions can make driving a car smoother and safer. Imagine you're trying to solve a puzzle. You have all the pieces, but putting them together requires careful thought and a step-by-step approach. Logical thinking in programming works in the same way. In this video, we will explain the principles of logical thinking in programming. Logical thinking in programming refers to the process of applying systematic reasoning to define a problem and arrive at a solution. Within the context of programming, developers most frequently use two primary logical thinking skills: deductive reasoning and problem decomposition. Let's start with deductive reasoning. Deductive reasoning is the process of drawing specific conclusions from general premises. Let's see how this works in programming. Deductive reasoning starts with premises. A premise is an assumption or fact used to draw a conclusion. Programmers use deductive reasoning to debug and fix issues more efficiently. For instance, let's assume you're debugging a system and discover a function that's causing unexpected behavior. You would approach the problem by working from two primary premises. The first is that all bugs cause unexpected behavior in the system, and the second is that this function is causing unexpected behavior. On the basis of these premises, you could draw the conclusion that this function must contain a bug. Programmers use deductive reasoning to gain a high-level understanding of how a problem should be solved. Once they have a high-level view of the problem, they can define a logical step-by-step approach for solving it. Next, let's look at the most commonly used step-by-step approaches to problem solving in programming. When you're presented with a problem, you most likely evaluate it and begin to strategize how you're going to solve it. A common approach is to look at a larger problem in terms of its constituent parts and make it easier to solve. This is called problem decomposition. There are two main approaches to problem decomposition: top-down and bottom-up. The top-down approach is a method of problem solving that begins with a broad overview of a problem and breaks it down into smaller, more manageable parts. The top-down approach is useful when you have a clear overview of a problem, but need to break it down to make it easier to manage. By using the top-down approach, you can decompose the problem into smaller atomic tasks that are more easily addressed. For example, if you're building an e-commerce website, you might focus on a high-level problem such as designing shopping cart functionality. Next, you would break down this functionality into smaller components, such as adding items to the cart, updating quantities, and processing payments. You would then continue by breaking down each of these into even smaller components, more specific items, until you arrive at manageable coding tasks. The top-down approach helps developers go from a big idea to specific tasks when developing software, but it's not always ideal in every situation. Sometimes the developer needs to gather more information when they're debugging or take a modular approach to software development. In these cases, they may prefer bottom-up approaches to solve the problem. Let's explore the bottom-up approach next. The bottom-up approach is a method of problem solving that starts with the most basic elements and combines them to create a broad composite. The bottom-up approach enables developers to explore problems or begin development without having a lot of information up front, and allows them to scale research and development efforts as needed. In our e-commerce example, you might start with the basic functions of adding items to the cart. Next, you would combine these functions to build larger components, such as the entire shopping cart module. And finally, you integrate these larger components to form the complete system and ensure that all the parts work together seamlessly. Let's bring this all together by considering the example of GrooveEco, a rapidly growing e-commerce company offering sustainable living products. GrooveEco's dev team has observed that their recently unveiled product recommendation engine has been plagued by low reliability. They apply logical thinking to work through this challenge, starting with these premises. Faulty algorithms cause errors, and errors lead to reliability issues. They then move on to conclude that the recommendation engine's low reliability is likely due to an error with an algorithm in the product's software. This helps them to identify a specific problem to focus on. They then break down this problem using a top-down approach, identifying the main recommendation algorithm as a potential culprit. They then decompose the algorithm into smaller functions for user behavior analysis and product matching. By individually addressing each smaller function, they are able to progressively hone in on and address the root cause, improving the overall recommendation system. In this video, you learned how to apply logical thinking and programming to help you solve problems efficiently and create robust solutions. By mastering deductive reasoning and problem decomposition, you can tackle any coding challenge problem systematically and effectively.
Every programmer, regardless of experience, encounters moments of frustration when errors seem impossible to solve. Even the legendary Grace Hopper, a pioneer in computing, faced such challenges. In 1947, while working on the Harvard Mark II computer, Hopper and her team discovered a moth trapped in a relay, causing the system to malfunction, a discovery that led to the coining of the term debugging. This story is more than just a historical anecdote. It symbolizes the universal and timeless struggle of debugging, an essential skill that separates effective programmers from the rest. In this video, we will explain the basic principles of debugging. Debugging is the process of identifying and resolving errors or bugs in a computer program. The thing to remember is that no code is ever completely error-free. Errors are a natural part of programming, and even the most experienced developers encounter them regularly. Let's start by looking at the first type of error you might encounter: syntax errors. Recall that syntax errors are mistakes in the code that violate the rules of the programming language. Syntax errors occur when you write code that doesn't follow the syntax rule of the programming language. These are usually caught by the compiler or interpreter. Now that we've defined syntax errors, let's look at an example in C# where a syntax error could arise. Suppose you have a method called start, and let's suppose you have a string called welcome message with an initial value of welcome to my web application. But you've forgotten to close the string properly by failing to add the final quotes in the string. When you try to compile this code, the compiler will give you an error similar to this: error CS1002, semicolon expected, error CS1513, bracket expected. This is because the compiler was expecting the initial quotes to be closed by writing the closing quotes and the closing brackets too. The compiler will be confused, and thus the code needs to be debugged. Fortunately, syntax errors are among the least of your concerns, as they typically are caught by the compiler. Modern code editors also often provide suggestions on how to fix them. Visual Studio Code will even provide a line number where the syntax error was found and put a red line under the code it thinks caused the error, even before you try to compile the code. Additionally, most editors now use color coding, which helps you spot errors visually. Something will often look off when there's a mistake. With time and practice, you'll start recognizing these errors even before you hit compile. Now that we've covered syntax errors, let's move on to runtime errors, which require a bit more knowledge and expertise to handle. Unlike syntax errors, which occur during the compilation phase, runtime errors occur during the program's execution. They often cause the program to crash or behave unexpectedly. Runtime errors happen when the program runs and it encounters an operation it cannot handle. These are typically caused by invalid operations or memory issues. To illustrate this, let's consider an example where a division operation can lead to a runtime error if not properly handled. Here we have a method called divide numbers that receives two parameters, the numerator and the denominator. The issue arises because the programmer has to use a basic division operation. If the code attempts to divide two numbers without proper error handling, a user might try to divide by 0, which, as we know, is impossible, and this will result in an error. This type of error is usually managed by the runtime environment, such as the .NET framework. However, these environments aren't always effective at handling these errors. They often cause the program to crash abruptly. So while runtime errors can be frustrating, they're usually obvious because the program fails, alerting you to the issue. The real challenge lies in the logical errors, those hidden mistakes that don't cause a crash, but silently produce incorrect results. Let's examine logical errors. Recall that these are mistakes in the program's logic that produces incorrect results but do not crash the program. Logical errors are often the hardest to spot because the code syntax is correct. So the compiler compiles, nothing crashes, and the code appears to work, but it produces incorrect results. Let's look at an example. Here we have a method called applied discount. It has two parameters, the price and the discount percentage. Suppose we make a logical error by incorrectly applying a discount percentage using subtraction instead of multiplication. The code will compile without syntax errors, and it will not produce any runtime errors. However, it is incorrect because it doesn't produce the right results. Invoking this method with $1,000 and a 50% discount should give you $850. But since the programmer wrongly used a formula with a subtraction, it will give $985, which is an error. Now that we've identified the different types of errors, let's explore how to diagnose and fix them with debugging techniques. The first tool in your debugging toolkit is breakpoints. Recall that breakpoints allow you to pause the execution of your code at specific points so you can inspect the state of the program. Setting breakpoints in your code can help you pause execution at critical points and examine variable values and program flow at different stages of your program. To use breakpoints in an IDE like Visual Studio Code, you set them in the line where you think something is happening or where you want to inspect what is happening more deeply. Remember that breakpoints do not work for syntax errors since they stop or break the execution when the program is running. Thus, breakpoints work for runtime and logical errors. After setting your breakpoints and pausing your code at critical points, the next step is to inspect the values of your variables. Inspecting variable values allows you to check the current values of variables at different points in your code. Once you've checked the values of the variables, you can step through the code. Stepping through your code allows you to execute your program one line at a time to closely observe its behavior. Stepping through your code line by line helps you understand how the program flows and where it might go wrong. But sometimes you need the code to run and print messages allowing you to examine their content. The classical way to do this is by printing error messages to the output so you can analyze them. Have you ever encountered an error in an app where the window comes up and tells you, oops, something failed, with a bunch of technical information that users often do not understand? Well, that's there because a programmer included a message printing of some sort. The most basic way to do this is to insert console.writeLine statements to print in a console. This can be useful if you want to inspect many variables simultaneously or just see the code flow in a single printing. Reading and understanding error messages can tell you where and why your code fails. When printing messages, pay close attention to the line numbers and descriptions in error messages to quickly locate and fix issues in your code. While traditional methods like reading error messages are valuable, there's an even more practical approach available in modern IDEs, the debugger's inspector. In this video, we have explored the basic principles of debugging. By understanding the common types of errors, such as syntax, runtime, and logical, you can better anticipate and address the issues that arise in your code. As you continue to practice and apply these techniques, you'll gain the confidence and skills needed to tackle any coding challenge that comes your way. Debugging is a valuable skill for every developer, ensuring that your code runs smoothly and efficiently. Mistakes in code are inevitable, but knowing how to identify and fix them can save time and prevent potential issues. In this video, we will learn to apply debugging techniques to identify and fix errors in code. Let's explore some tools that can aid your debugging efforts. One of the go-to tools for many developers is Visual Studio Code. Here's a common scenario, a simple piece of code that divides two numbers. Everything seems correct on the compiler. Variable names are clear and commas and semicolons are in the right places. As a result, the compiler doesn't flag any syntax errors, meaning there's nothing wrong with the code structure or formatting. However, if this code runs and the user passes 0 as the denominator argument, a runtime error will occur. You will find a runtime error only when the program executes. The error would occur in this case because having a 0 in the denominator is a mathematical impossibility. To fix this, many programmers use a debugger. A debugger is a tool that helps developers find and fix errors or bugs in their code. It allows you to run your code step by step, inspect variables, and understand the flow of execution to identify where things go wrong. One of the most popular debuggers front-end developers use is integrated into Visual Studio Code, VS Code, and you can access it through the debugger button in the top right corner. In the VS Code debugger, you can set breakpoints to stop the program's execution, watch variables, and step through your code to understand exactly how it runs. This makes VS Code a powerful tool for quickly identifying and fixing errors, which improves your code's quality and reliability. Let's find out how this works in our example where we're dividing two numbers. We built our divide numbers method. It gets two parameters and returns their quotient. In this example, we'll execute this code and call the method with a 0 in the denominator. To do this, I store the result in a variable called result. Here we are dividing the numerator 10 with the denominator 0, and then we print the result. The code compiles, so there aren't any syntax errors. But when I run the program, it shows the result is and then an infinite sign. This is a runtime error. When faced with an error like this, you can count on several debugger features to help you debug the code. The first one is breakpoints. Here's the code for the divide numbers method. In VS Code, you can set breakpoints by clicking in the gutter next to the line number where you want to pause the execution. We can add a breakpoint in this line. The next time the program runs this line, it will stop before executing, so you can determine what may be happening before this breakpoint. In general, you want to add breakpoints on the lines where your variables change so you can inspect their values later and review whether they are as expected. After setting your breakpoints, the next step is inspecting your variables. This is where you can determine exactly what's happening in your code at that precise moment when the breakpoint is hit. Checking the values of variables during execution helps you verify that your program is manipulating data as expected. The debugger includes a tool called the inspector. You can use it to hover over a variable to reveal what value it's holding. In this case, the denominator has a 0. Once you have checked the variables, you can manually move to the following line using the Step Through Code feature in the debugger. This lets you move through the code line by line using the toolbar controls to follow exactly how things are flowing and to catch where things might be going wrong. The debugger toolbar shows a set of buttons that you can use. The first button is Continue, which resumes program execution until the next breakpoint is hit or the program ends. The next button is Step Over, which executes the current line of code and moves to the next line, but does not enter into functions or method called by that line. Then the Step Into button. This executes the current line of code and, if the line contains a function or method, enters into that function to allow line-by-line debugging inside it. Next, the Step Out button, which completes the execution of the current function and returns to the calling function, then pauses. Then the Restart button, which stops the current debugging session and starts it again from the beginning. Finally, the Stop button ends the current debugging session entirely, halting all code execution. Stepping through code works once the debugger has stopped the execution as mandated by a breakpoint. In this example, I've added a variable called result because I want to inspect the result of the operation. To do so, I've added a breakpoint in this line. At this point, you can inspect the variables and check what is happening inside your code. If you want, you can step through it to find out exactly where the error occurs. In this case, we notice the variable result has a 0, which would cause the error we're investigating. Stepping through the code allows you to pinpoint exactly where issues occur. For example, when I step over this line and inspect the variable now, I get the odd result of having a value of infinity, which was the unexpected behavior to begin with. With the right focus, you can locate the errors in your code. Using the debugger's inspector will help you understand the values of variables to get more information on them. In this video, we explore the importance of debugging techniques to efficiently identify and fix errors in your code. We've used the Visual Studio Code debugger, which allows you to set breakpoints, inspect variables, and step through your code, providing a powerful way to understand and resolve issues. By mastering these tools and techniques, you'll enhance your problem-solving abilities and become a more confident, efficient programmer. When learning a new programming language, getting the structure and syntax right from the beginning can be the difference between smooth progress and countless hours of troubleshooting. When starting with C#, understanding how each part of the program fits together is essential to writing clean, functional code. Mastering these basics now will set the foundation for everything you build moving forward. In this video, we will explain the fundamental syntax and structure of C# programs. We'll cover key concepts such as classes, variables, control structures, and methods. We'll also explore some simple code examples to illustrate these concepts. First, let's examine the structure of a basic C# program. C# programs start with a class definition and contain methods where the actual logic resides. This C# code block defines the program class, which contains all the executable code. The static void main method serves as the entry point for the program. The braces define the blocks of code for the class and method. The console.writeLine command outputs the text "Hello World" to the console. This is the program's body where the work is done. Next, we'll examine variables, which are used to store data that can be used and manipulated within the program. Variables need to be declared with a type keyword that tells the program what kind of data the variable holds. There is an exception which we'll examine shortly. This sample code declares 4 different variables and initializes them with a value. First, int age equals 25 declares an integer variable called age and assigns it the value 25. Integer data types can only hold data that are whole numbers. The second variable, name, we declare with the string data type. We also assign the text John to the name variable. String variables can only hold text data. Our final 2 variables use a special type keyword, var. These variables don't declare a type up front. Rather, C# determines what type of value the variable holds when the program runs. In this example, we have one variable count that is initialized with the integer 10, and another variable message that is initialized with the string value hello. Both are declared with the type keyword var. Now let's examine how to create control structures in C#. Control structures manage the flow of the program. The most common control structures are if statements and loops. These structures help the program make decisions and repeat actions. We'll start with the if-else statement, which evaluates true-false conditions. In this sample code, the statement if age is greater than or equal to 18 checks whether age is greater than or equal to 18. Notice that we use the greater than and equal signs together to check whether the age is 18 or greater, and not just greater than 18. If that statement is true, the program prints, "You're an adult." If that statement is false, the program moves to the code in the else section of the code and prints, "You're a minor." This structure allows the program to take different actions based on the condition. The next type of control structure is the loop, which you can use to run the same block of code repeatedly. Let's examine how loops work in C#. In C#, a for loop is defined with the for keyword. The code you want to run repeatedly is put between the curly braces. Then we define the conditions for the loop in the parentheses after the declaration keyword. In this code sample, we first initialize the iterator, I, to 0. This sets the starting value of the loop. Then we set the condition for when the loop will exit. Here we tell the loop to run only as long as I is less than 5. Finally, we use the code I++ to add 1 to the variable I each time through the loop. Inside the loop, we write the code console.writeLine I, which prints the value of I to the console. This sample will print the numbers 0 to 4 to the console. Methods are the final concept we'll examine. Methods are functions that exist and work in classes in an object-oriented language like C#. They are blocks of code that perform specific tasks. They can take parameters and return values. This helps organize the code and make it reusable. Let's investigate how they work and how they're constructed. In this code sample, we create a class called calculator. We can add code to this class that can perform all the operations of a calculator. By adding that functionality to a class, we group code that does similar work into one place and give it the ability to work together. The class has 2 member variables called number1 and number2 that have the int data type. These are declared as private since they'll only be used by the methods in the class. For this example, we'll add one method to the class called add, which is declared as an int. Declaring the method this way means that the value the method returns to the code that called it has to be an int data type. Because we're adding numbers, we implemented two integer parameters. These are the data that we'll pass into the method. Now we'll assign the member variables to the value of the input parameters in the add method. Because the member variables were declared as a part of the class, the method can use them to do its work. This is one of the differences between a method and a function. A method can use members of the class and a function cannot. Finally, the body of the method sums the values of the parameters number1 and number2 and returns the result. This method operates similarly to a function by processing data and returning a result. But you'll notice that it works inside a class and can interact with and operate on other class members. Now let's bring all these concepts together by building on our calculator program. We'll use a similar class and method from the previous example and declare the calculator class that includes the add method. Next, we'll add a second static method called main. We'll declare main with a void return value since this method doesn't take input parameters or return a value. Now we'll add two member variables, num1 and num2, declared as the type integer. We'll initialize num1 with the value 5 and num2 with the value 10. Next, we declare a variable called result with the type int. We'll set its value to the result of the add method. We pass in the values of num1 and num2 as parameters for the add method. Finally, we use console.writeLine to print the value of the result variable to the console. In this example, the result will be 15, so the console will show the sum is 15. We've now covered the basic syntax and structure of C# programs. We examined the structure of our program, explored variables and data types, examined control structures, and discussed methods. We also created a simple calculator program to tie everything together. These building blocks are essential for writing more complex C# applications.
Writing and executing code is one of the most effective ways to understand programming. In this lesson, you'll see how C# comes together as we dive into creating simple programs. We'll cover the essential steps to write and run your own C# code, giving you a solid foundation to build on as you continue your journey into the world of programming. Let's get started and see how these concepts come to life in practice. In this video, we will write and execute simple C# programs. We will write and run simple C# programs to apply the concepts we've learned. These programs include a basic calculator, a loop to display numbers, and a method to process user input. Let's start with something straightforward, a basic calculator. We'll use this program to perform simple arithmetic operations like addition and subtraction. Ready? Let's get started. To get started, we'll need to define a class called calculator. This is where we'll house the methods for performing addition and subtraction. Let's go ahead and set that up. For this, we'll start by creating a class with public class calculator and adding the brackets, which will include methods for addition and subtraction. Now that our class is set, the next step is to declare some variables. These will hold the numbers we're going to work with. Let's add those in now. For now, our calculator will operate on two numbers, so we will define them as this. Int, as they will be integers. Just to make it simpler, we used number 1 for the variable name. The system will initialize it automatically at 0. We do the same for the second variable, called number 2. With our variables in place, it's time to write a method that does the actual math. We'll create a method that takes two numbers as inputs and returns their sum. For this, we've created a method called add that sums number 1 and number 2 and returns the result. Now that we've got our method ready, it's time to see it in action. To do that, we'll need to write the main method inside our calculator class. This is where it all comes together. Let's take a look at how it works. We've written the main method, which remember is the starting point of the program. This method is quite simple. In this method, I assign 5 to the number 1 variable and 10 to the number 2 variable. Then I created a variable called result to store the return of the add method. And I called the method immediately by saying add and these parentheses. Then I went ahead and used this statement, console.writeLine, passing the concatenation of sum and the result from the add method. we would expect it to show 15 as the result. If you run this code, it should write something like this in the terminal, sum:15, which is the expected result. Now try adding other pairs of numbers and see if the result is what you'd expect. You can also try to create a subtraction method in the same fashion. Let's pause for a moment to discuss the static keyword we've been using in our variables and methods. The static keyword allows a variable or method to be accessible throughout the program without needing to create an instance of the class. We'll continue using static for now since we haven't covered objects yet, but keep in mind that it's a useful tool for keeping your code straightforward and accessible. Let's move on to something a bit different. Our next task is to write a program that displays numbers from 1 to 10 using a loop. Think of it like setting up a countdown timer or listing the steps in a process. You repeat similar actions over and over until you reach the end. This will show us how to control the flow of our program. Let's get started. Again, start by defining a class named NumberDisplay. Next, write the loop method to display the number. In this case, we're using a for control structure. I've created an index that initializes with an int I that starts at 1, and it iterates while I is less than or equal to 10. It always increments by 1 on each step, noted by the ++. And on the for's body, we just print the index number with this console.writeLine. As in the previous example, we will define a main method as the starting point of our program. Write the main method to call the display numbers method. And just a quick detail before we move on. As you may have noticed, the main method does not return int, but the word void. Void is a data type in C# that just means nothing. It is used when the method does not return anything. When you run this program, you will get a list of numbers from 1 to 10. Try to change the number of times the display numbers method iterates to see what happens next. The result should show you a list of numbers from 1 to the number of times you chose. So far, we've been running programs without any input from users. They just run as written with no changes to the variables. But imagine creating a survey or a game where users enter their choices. That's where handling user inputs becomes crucial. It's one of the most important parts of programming because it allows your program to interact with people in real time. Let's explore how we can make that happen. Start by defining a class named userInput. I've written a method called greetUser that starts by asking a user to enter your name using a console writeLine. Next, we are declaring a variable with the string data type that can hold strings of characters, such as a name. Then we use the method console.readLine, which detects characters in the terminal until the user hits the enter key. The program then greets you by saying hello and then your name. As usual, we write a main method to call the greetUser method. When you run this program, it will ask you for your name and greet you. Let's say I type my name here and hit enter, and then the program will greet me. Hello, computer. Nice to meet you. In this video, we have written and executed simple C# programs, allowing you to apply the concepts we've covered so far, from creating a basic calculator and displaying numbers with a loop to handling user input. These exercises have provided a hands-on approach to understanding C# syntax and structure. As you continue practicing, you'll find that writing and running your own code becomes increasingly intuitive, laying a solid foundation for more advanced programming tasks. Keep experimenting with these examples, and soon you'll be able to build more complex and dynamic C# applications with confidence.
In this first step, we will create a simple calculator program that performs basic arithmetic operations such as addition and subtraction. We will start by defining a class and writing a method to add two numbers. In C#, a class is like a container for your program's code. It holds methods, which are sets of instructions that tell the program what to do. Think of a method like a recipe that the program follows step by step. Here we're going to add a method called add, which will add two numbers together. The word static means the method belongs to the class itself, and public means it can be accessed from other parts of the program. A variable is like a container that holds data that your program can use. Here we have two variables called number1 and number2 that will store the numbers we want to add. The method will return the result using the return keyword, which means the method sends the answer back to the part of code that called it. Now that we've created the add method, it's time to see how it works. To execute a C# program, we need to write a main method, which is the entry port of the program. This is where everything comes together. In C#, every program starts by running the main method, which is like the starting point of the program. When you run a C# program, the code inside main is the first to execute. In this case, inside main, we're going to assign values to number 1 and number 2, call the add method to calculate the sum, and use console.writeLine to print the results on the screen. Calling a method means running the code inside the method and using its result. Next, we will write a program that uses a loop to display numbers from 1 to 10. Loops are control structures that allow you to repeat actions multiple times. A for loop is used when we know how many times we want to repeat a block of code. In this case, we want to print numbers from 1 to 10. The loop has 3 parts. Initialization, int I equals 1. This sets the starting point for the loop. We start with I equals 1. Condition, I is less than or equal to 10. This tells the loop when to stop. As long as I is less than or equal to 10, the loop will run. When I becomes 11, the loop will stop. Increment, I++. This increases the value of I by 1 after each loop iteration, so the next number is printed. Now let's write a program that interacts with the user. This program will prompt the user for their name and greet them. Handling user input is important for creating interactive programs. In this step, we'll interact with the user by asking for their name. To capture the user's input, we use console.readLine. This waits for the user to type something and then stores that input as a string, which is a sequence of characters like a word or sentence. We store the user's input in a variable called name. Once we have the user's name stored in name, we can use console.writeLine to display a personalized greeting. Notice that we first prompt the user to enter their name with console.writeLine. After the user types their name, it is stored in the name variable using console.readLine. We then use that variable to greet the user by name, showing how input can be used dynamically. Console.readLine is useful for capturing input, while console.writeLine is used to display messages to the user. We will create a small console application that allows users to manage a simple to-do list. The program will let users add tasks, view the list of tasks, and mark tasks as completed. This will involve collecting user input, storing the data in an array, and using loops to interact with the list. When building a program, it's helpful to break it down into smaller tasks, which makes it easier to write and understand. In this program, we will add tasks to a list, view tasks to see what's on the list, mark tasks as completed when they're finished. To do this, we will use methods, loops, and arrays. Each part of the program will have its own task to perform, making it easier to work with. Arrays are useful because they allow us to store multiple tasks, and loops allow us to repeatedly check what the user wants to do next. Finally, we'll use debugging techniques to catch and fix any mistakes we might make. First, we need a place to store the tasks. We will use an array, which is a special type of variable that can store multiple pieces of data. Arrays are useful when we want to store several things of the same type. In C#, an array is like a container that holds several values of the same type. In our case, the array will hold strings, which are pieces of text representing the tasks. Arrays have a fixed size, in this case 10 tasks, which means we can only store up to the 10 tasks in the array. Each task will be stored in a separate spot called an index. We access each task in the array using an index which starts counting from 0. We'll also need a counter variable called task count to keep track of how many tasks are in the list. This variable starts at 0 because the list is empty at first. Each time a task is added, task count will be increased by 1, making sure the next task is stored in the next available spot in the array. Next, we will create a method to let the user add tasks to the list. When the user types in a new task, we will store it in the array at the correct position using the task count variable. We'll use a method called addTask to ask the user to enter a task. The method will store this task in the array using console.readLine, which captures what the user types. The task will be saved in the next available spot in the array, which is determined by task count. Remember, arrays start at index 0, so the first task will be stored in tasks 0, the second in tasks 1, and so on. After each task is added, we increase task count by 1 to make sure the next task goes into the next available spot. This ensures that every new task is added to the right spot and we don't overwrite any existing tasks. The task count variable helps us keep track of how many tasks have been added and where the next one should go. Now we will create a method to display all the tasks the user has added so far. This method will loop through the tasks array and print each task. To view the tasks, we'll use a loop to go through each element in the tasks array. The loop will start at index 0, the beginning of the array, and will stop once it reaches task count. This ensures that we only print the tasks that have been added and avoid printing empty spots in the array. Each task will be printed with a number starting from 1 for easier reading, even though array indices start from 0. The number I plus 1 is used to make this more user-friendly. Now we'll create a method to let the user mark a task as completed. This will allow the user to update a task in the array and show it has been finished. The user will choose a task to mark as completed by entering the task's number. Arrays in C# start counting from 0, but the user will enter a number starting from 1. So we need to subtract 1 from their input to get the correct index in the array. For example, if the user selects task 1, we need to update tasks 0. Once we find the correct task in the array, we will modify it by adding the text completed to show it is finished. This will update the task and make it clear to the user that it has been marked as complete. Finally, we will write the main method that brings everything together. This method will let the user decide whether to add a task, view tasks, or mark a task as completed. We'll use a while loop to keep the program running until the user decides to quit. Inside the loop, the program will show a menu of options. The user can select an option to add a task, view task, or mark a task as complete. We'll use a switch statement to handle the user's input, calling the right method based on their choice. The loop will continue until the user selects the option to exit the program. In this step, we will introduce a common error that can happen in your program and walk through the process of finding and fixing it. Debugging is an important skill, and learning how to identify and solve problems in your code will make you a better programmer. Let's say the user tries to mark a task as completed, but they enter a number that is outside the range of the task list. For example, they enter 12, but there are only 3 tasks. This will cause an index out of range error because the program tries to access a part of the array that doesn't exist. Let's explore how we can debug and fix this problem. An index out of range error occurs when your program tries to access a position in an array that doesn't exist. For example, if your array has 3 tasks and the user tries to mark task 4 as complete, the program will crash because there is no task at that position. To prevent this, we can use error checking to make sure the user's input is within the correct range. To fix this error, we'll print the value of task number before accessing the array to check if it's correct. Then we will update the code to give the user an error message if they enter a number outside the range of the tasks. Once you've added the debugging line and handled the error, your program no longer should crash when the users enter an invalid task number. Instead, it should display an error message like, "Invalid task number, please try again."
As you have discovered, mastering programming fundamentals is crucial for developing effective code. To strengthen your foundational understanding, we began by reviewing fundamental programming concepts, including variables, data types, control structures, loops, methods, and pseudocode. Then, we combined logical thinking with core programming principles to help sharpen your problem-solving skills. Next, we covered fundamental debugging techniques and tools to help you detect and resolve errors in your code. Then we practiced building straightforward programs in C# using your foundational knowledge to create functional code. And finally, we worked on a project that combined all the concepts and debugging techniques, providing hands-on experience in applying your skills to a full development task. Mastering programming fundamentals is essential to creating reliable and efficient code. By honing these skills from understanding core concepts to debugging and building C# programs, you'll enhance your ability to tackle complex development tasks and deliver high-quality applications.
Welcome to Mastering Object-Oriented Programming in C#. This module covers the core concepts of objects, classes, inheritance, and polymorphism, and demonstrates how to apply them in C#. You'll also learn key design patterns and practices, implementing them strengthening your programming skills. We will begin by defining objects and classes and understanding their role as the foundation of object-oriented programming. You'll learn how these elements create a structured, reusable code base. Next, we'll examine inheritance and polymorphism, exploring how they allow flexibility and scalability in your applications. We'll break down their functions and importance in OOP. Then we'll apply these concepts in C# with practical examples, helping you see how they work in real-world scenarios. You'll gain hands-on experience to deepen your knowledge. After that, we'll explore common design patterns in OOP and identify how they provide solutions to recurring development challenges. You'll learn when and how to apply these patterns effectively. Finally, we'll implement classes and objects in C# through guided exercises, reinforcing your skills and confidence in applying OOP techniques. By the end of this module, you'll have the knowledge and practical skills to apply object-oriented programming principles in C# confidently. Let's get started with mastering object-oriented programming in C#. One of the disciplines in biology is classification. Scientists use specific properties to group animals to create classes like zebras, pelicans, and humans. Within these classes are individual zebras, pelicans, and humans that share properties of other members of the class, like stripes, beaks, and opposable thumbs. Classification helps scientists manage their research, understand how animals are similar and different, and even know what to expect from their behavior. Computer scientists have applied many of these concepts in a programming model called Object-Oriented Programming, or OOP. In this video, we will explain the basic concepts of objects and classes in OOP. Objects and classes are the fundamental coding building blocks of object-oriented programming. Code-based classes and objects are related in the same way that an animal is related to the class in which it belongs. Think of an object as an individual thing or an instance of a class, like a particular zebra. The class is a type of definition. It describes all the properties and abilities that the average zebra has. Let's explore these concepts in more detail, starting with the definition of a class. A class is a blueprint or template that defines a set of shared characteristics and behaviors for a group of things. Code classes are similar to classes in biology or botany in that they define the properties of the individual code objects and what they can do. Classes in object-oriented programming by themselves can't do much work. A programmer can't process data, interact with the user, or send API calls. But a class provides a blueprint for how to do all these things. Specifically, a class has three main features that define them. The first feature developers define in classes are properties. These are the individual items of data that an object stores or sets. For example, an authentication class may define properties like username and password. Classes also define methods, which are also referred to as behaviors or functions. Methods are the behaviors the class can perform. For example, the login class may define methods like validate, which checks the user's credentials, and login, which gives the user access to the system. Finally, through a feature called inheritance, classes can be extended to create subclasses that inherit properties and behaviors from the parent class, just like offspring in biology. This feature enables the developer to reuse and better organize code. For example, a developer may inherit the login class, reusing its properties and methods, but adding a new attribute called displayName that they can show on a user interface after the user has logged in. Because classes are definitions only, in order for them to do work, developers have to create a working version of them. This is called instantiation, and the process creates individual objects or instances of the class. An object is a distinct thing that possesses unique properties and behaviors that define its characteristics and actions. Code objects, like other types of objects, are defined by their properties and the things they can do within a program. Code objects have all the properties and methods of the class of which they are an instance. The object's properties are the data elements associated with the object defined by variables within the class. Its methods are the operations or functions the object can perform, defined by the methods in the class. Objects also have a couple of other features that differentiate them from the parent classes. Each object has a unique identity within the program, often represented by its memory address or a unique identifier. Because objects are instances of classes, the developer can create as many as they need, and each one is uniquely identified in the application. The object's state is determined by the current values of its properties. For example, a login object's state might include the values it currently holds for username and displayName. An object can only do what is defined in its parent class unless a developer uses inheritance to extend the class. Then an object created with an inherited class will have all the new properties and methods, as well as the original one from the parent. Now let's bring these ideas together using an example of a book class that might be used in a library system. The book class might have properties like title, author, and ISBN. It might also have methods like borrow and return. By defining these properties and methods, we can create specific book objects, each representing a particular book in the library with its own title, author, and ISBN. When a book is borrowed, the borrow method can update the status of the book, demonstrating how properties and methods work together to manage the state and behavior of objects in OOP. Object-oriented programming is an efficient and powerful programming model. By defining classes and creating objects, developers can write code that's more easily maintainable and reusable. Just as you don't need to understand the inner workings of a post office to use its services, developers don't need to know the internal details of a class to interact with it. Developers use the principles of encapsulation and abstraction to simplify how their code is used. In this video, you'll learn how to explain the principles of encapsulation and abstraction in object-oriented programming, and how these protect the internal state of an object and simplify its use. Let's start with encapsulation. Encapsulation is the principle of bundling methods and data into a class and restricting access to some of the class's components. This is done by managing the interfaces through which the class's data can be accessed and modified. When developers apply this principle, they keep an object's internal state hidden from outside code, exposing only what is necessary. Let's examine more closely how developers use this principle to create classes. Encapsulation protects an object's internal state by managing access to its attributes and methods. Developers use access modifiers like private, protected, and public to manage what data and methods other code has access to and how data can be modified. For example, suppose a bank developed an application and the code has a bank account class that includes data and methods for managing data related to a customer's account. The balance attribute stores the customer's account balance data. The developer might provide a public getBalance method that lets other code read the attribute, but no method for writing to the attribute. Encapsulation allows developers to expose parts of the object to any of the application's code using public methods. They also can expose other parts only to parts of the app that inherit from the class using protected methods. These principles give the developer fine-tuned control on which parts of the class are exposed and how broadly. Suppose the bank account class has an interest rate attribute that stores the interest rate the bank currently applies to the account. The developer doesn't want the interest rate attribute exposed, so they create no method for accessing it. However, they do want people to be able to make deposits and withdrawals, and so they provide public methods that enable these activities. Encapsulation is a principle that focuses on managing the data and methods of the class. It helps developers protect parts of the class they want to keep secure and expose the part that the rest of the application can use. Another principle of object-oriented programming, abstraction, defines what methods a class should implement without providing specific implementation details. Let's explore that next. Abstraction is the principle of defining what an object does but not specifying how it does it. Developers achieve this by creating abstract classes and interfaces. When developers apply this principle, they define an object's essential features and behaviors, but enable developers to decide how methods within those objects are implemented. Let's examine more closely how developers use abstraction to create objects. Developers can apply the principle of abstraction in two primary ways. They can use an abstract class when they want to share a common code base with concrete methods, which are methods that include the implementation code. But they also can include abstract methods that just define the interface, but don't provide any implementation details. Developers can also create interfaces that do not include concrete methods. You can think of an interface like a contract that defines a set of methods that an inherited class must implement. Interfaces typically only include what methods an inherited class must implement, but not the implementation code. Suppose in the banking application, the development team creates an abstract class for handling deposits and withdrawals. This class defines an amount attribute and declares the abstract methods for deposit and withdrawal. The savings account functionality inherits from this abstract class and provides specific logic for how deposits and withdrawals should be handled. The checking account code does the same. Any other part of the app that interacts with these accounts knows that both savings and checking will have deposits and withdrawal methods, without needing to be concerned with their implementation details. Now let's look at how the principles of encapsulation and abstraction work together. Suppose a library creates software to manage its inventory. The software's programmers create a library class that encapsulates data about books and patrons. It hides the internal data structures using private attributes and provides public methods like addBook and borrowBook. This protects the integrity of the library's data while allowing controlled access. Additionally, it uses abstraction by defining an interface catalog that exposes methods like searchBook and list available books. Any class that inherits from catalog implements its methods, making the system easier to use and maintain. In this video, you learned how to explain the principles of encapsulation and abstraction in object-oriented programming, and how these protect the internal state of an object and simplify its use. Encapsulation protects the internal state of an object by bundling data and methods within a class. Abstraction helps developers create consistent, predictable yet flexible classes. Applying these principles, developers can write secure and maintainable code. Have you ever wished you could take something old and make it better without starting from scratch? Object-oriented programming addresses this through the concept of inheritance, which enables developers to reuse code, but modify it and extend it only as needed. In this video, we will describe the concept of inheritance in object-oriented programming. Let's begin with the definition of inheritance. Inheritance is a fundamental concept in object-oriented programming that enables developers to create new classes based on existing ones. Similar to an inheritance in biology, code inheritance enables classes to inherit features from other classes. It allows a new class, known as a derived class, to inherit attributes and methods from the existing class. This is called the superclass or base class. When a developer creates a derived class, they get the attributes and methods of the base class, but also can extend their class by adding their own attributes and methods. This allows the developer to reuse the code from the base class without having to reproduce it. They also can add more features to the class and even modify the original attributes and methods if they need to. The new and modified features are isolated to the derived class and don't impact the base class. The relationship between the derived class and the base class is similar to the relationship between a child and a parent. The child may have many similar features of the parent, such as skin color, nose shape, and height, but the child will develop unique characteristics such as hair color and personality. This relationship creates a hierarchy in code that fosters reuse. It also allows developers to organize and manage code more efficiently. Inheritance creates a tree-like structure between classes. For instance, a bird class can be a base class for eagle and parrot derived classes. Both eagle and parrot will inherit common attributes and methods from bird, like fly, but can also have their own unique properties. The eagle-derived class may include a hunt method, and the parrot-derived class could include a speak method. The additional methods do not become a part of the base class, but remain isolated to the derived classes. By using inheritance, developers can reuse existing code and extend it with additional functionality. This promotes code reuse and reduces redundancy. In this video, you learned to describe the concept of inheritance in object-oriented programming. Inheritance enables developers to inherit properties and methods from existing classes and create hierarchical relationships. By applying this concept to their applications, developers can write efficient and organized code by promoting reuse and extension of existing functionalities. Imagine having a blueprint for a house that can be reused and modified to build different types of houses. Inheritance in programming works similarly, using properties and methods from an already existing class. In this video, we will apply inheritance in C# programs. By using inheritance in C#, developers can create a new class that inherits properties and methods from an existing class. The existing class is called the base class, and the new class is called the derived class. To begin, C# developers define a base class by using an access modifier. These keywords determine whether other parts of the code can access the class. Declaring a class as public means its members are accessible from any other class. Private class members are only accessible within the class itself, and protected members are accessible within the class and by derived classes. After the access modifier, the developer uses the class keyword followed by the name of the class to finish the declaration. The base class contains common properties and methods that other classes can inherit. Properties hold data that the class will use internally to guide how it functions, or data that the class will process. The methods define the work the class can perform. Finally, the base class has a constructor, which is the entry point for the class. It's like the front door of a house where you enter and declare who you are and why you're there. The constructor can take input parameters which the developer can use to set the initial values for the class's properties. Let's explore an example. Suppose a developer wants to create a class that manages maintenance information for a pool. They declare the class as public, and it has two properties, chlorine level and water level. The constructor takes these values as input parameters and assigns them to properties. This simple class has a method called poolInfo that writes out the values that were passed into the constructor. This class has all the elements of a base class and can be easily expanded with more properties and methods to make the class a lot more powerful. Developers can further extend what a class can do by creating a derived class. A derived class inherits all the properties and methods of the base class, and developers can extend it without impacting the original base class. Let's examine how this works. Derived classes are defined similarly to base classes in C# by using an access modifier and a name for the derived class. To create a derived class, the developer follows the name by a colon and includes the name of the base class in the declaration. The derived class inherits all the properties and methods of the base class. Developers also can add their own new properties and methods. They get all the advantages of the base class, but can customize it for a particular scenario. For example, a developer can create a derived class for a spa from the pool base class. They declare the derived class with the public modifier and name of the class spa, which is derived from the pool base class. The derived class has the chlorine level and water level properties that the base class has, but the developer decides to add a new property called heat level since spas are heated. The constructor takes data for all three properties as input parameters and assigns them to the derived class's properties. This derived class uses the poolInfo method it inherited from the base class to display the spa's information on the screen. In conclusion, inheritance in C# is a powerful object-oriented tool that enables developers to reuse code and make it easier to maintain C# code. In this video, you learn to apply inheritance in C# programs. Inheritance in C# involves creating a base class and then deriving a derived class using inheritance. By using inheritance, developers build organized, reusable, and maintainable code in C#. Imagine a single tool that can transform into different instruments depending on the task at hand. That's the power of polymorphism in programming. In this video, we will apply polymorphism in C# programs. Let's begin by defining polymorphism. Polymorphism enables developers to use a single method name to perform different tasks based on the type of object it's acting on. Essentially, this means a method with the same name can do different work depending on what it's being asked to do. Next, let's explore a few ways that developers can apply polymorphism in C#. Developers use polymorphism in C# by creating a virtual method in a base class. This indicates that the method can be overridden. Method overriding allows a subclass to provide a specific implementation of a method that is defined in its base class. Let's explore an example. Suppose a developer wants to create a class that manages musical instruments. They declare the class as public, and it has a virtual method called play, declared as public virtual void play, that writes the message playing an instrument to the console when it's called. This class has a single virtual method that can be overridden by a subclass. These base classes also contain concrete methods which can't be overridden. To override the play method, the developer creates a subclass called piano that is inherited from the base class instrument. They create the play method using the override keyword, which is declared as public override void play. The overridden method prints the message the piano is playing to the console. A class could be created for other instruments in the same way, and each class would have a play method. Virtual methods aren't the only way developers can use polymorphism in C#. Developers can also create interfaces that do not include the method's implementation. You might be wondering, what is an interface? Well, an interface is a contract that defines a set of methods that an inherited class must implement. Interfaces typically only include what methods an inherited class must implement, but not the implementation code. For example, a developer creates an interface for the musical instrument play using the declaration public interface iPlayable. The method includes an empty method called play, which a subclass can use to create a concrete method that does work. To implement this interface, the developer creates subclasses called guitar and piano that are inherited from the interface iPlayable. Then, they create the play method, which is declared as public void play. The method writes the message the guitar is playing for the guitar subclass, and the message the piano is playing for the piano subclass. The use of interfaces promotes the consistent use of methods across different classes. In closing, developers should use virtual methods in C# when designing base classes when they want to include implementation detail for the subclasses. Interfaces in C# are best for scenarios where developers want to provide a basic set of methods a subclass must implement without the need to provide detail on what those methods might include. Both are powerful ways to use polymorphism in C#. Apply polymorphism in C# programs. We explored how to apply polymorphism by overriding methods and using interfaces. Understanding polymorphism helps developers write flexible and reusable code in C#. We'll start by creating a base class called Animal and two derived classes, Dog and Cat. This will introduce you to the concept of inheritance, where Dog and Cat will inherit properties and methods from Animal. Inheritance allows you to create a general class, Animal, that can be used as a base for more specific classes, Dog and Cat. This helps us avoid repeating code because common properties and methods are defined in the base class. For example, all animals might make a sound, but each animal makes a different sound. In our program, the animal class will have a method called makeSound that each specific animal class can override to provide its own sound. When we want to allow a method in the base class to be overridden in a derived class, we use the virtual keyword. This tells C# that the method in the base class is meant to be overridden in any class that inherits from it. The derived classes, dog and cat, then use the override keyword to provide their own implementation of the makeSound method. This allows each derived class to customize the behavior of the method. Think of virtual as giving permission to change how something works in the base class, and override is actually making that change in the derived class. In this step, we will call the derived classes from our program class using the main method as the entry point into the application. In the main method, we instantiate a dog object and a cat object using the new keyword. Once objects are instantiated, we can call any public method on those objects that we've defined in the class. We then call the makeSound method in each object, which should print the associated output to the console. We don't need input parameters for the makeSound method since the output is defined in the derived classes themselves. Now we will introduce interfaces which allow us to define a contract that classes can implement. This is different from inheritance but can be used alongside it. An interface is like a contract that classes can agree to follow. It defines methods that must be implemented by any class that implements the interface. Unlike classes, interfaces do not provide any implementation details. They only define what methods must be provided. Interfaces are useful because they allow us to specify a set of methods that different classes must have, even if those classes are not related through inheritance. For example, if we have an interface iAnimal with the method eat, any class that implements iAnimal must provide an implementation for eat, ensuring that all animals have this method. Interfaces provide a way to guarantee that certain methods will exist on any class that implements them. In this step, we will use polymorphism to interact with objects of different classes through a common base type or interface. This allows us to call methods on different objects in a unified way. Polymorphism allows us to treat different objects as if they are instances of the same class or interface. This is powerful because it lets us write code that can work with any class that shares a common base class or interface. For example, we can create a list of animal objects which include instances of dog and cat. When we call makeSound on each object in the list, the correct version of the method is called for each specific object. This works because both dog and cat override the makeSound method from the animal base class. Polymorphism is like a universal tool that lets you interact with different objects in a standardized way, regardless of the specific type. This is particularly useful when you want to work with a group of objects that share a common interface or base class but behave differently. Imagine working on a complex project where you constantly face the same challenges. Over time, you develop smart, repeatable solutions that make your work easier and more efficient. In software development, we call these repeatable solutions design patterns. They are tried and tested ways to structure your code, making it more efficient and scalable. In this video, you will learn to recognize and describe common design patterns. Design patterns are like reusable solutions for common problems in software design. They give you a standard way to tackle architectural challenges, making your code more reliable and easier to maintain. There are many design patterns that developers use to design their software. We'll explore a few of the most common. First, let's discuss singleton pattern, which ensures that a class has only one instance throughout your application and provides a single point of access to that instance from anywhere in your code. Developers use the singleton pattern to manage shared resources. For example, a database class can implement the singleton pattern to ensure there is only one connection to the database throughout the application. To implement this in C#, a developer creates a public class called database. They create a private variable that holds the instance of the database object and a private constructor that writes database connection established to the console when it's called. The developer then creates a public method called getInstance that assigns the private variable to a new instance of the database object and returns that instance to the code that called it. But before it assigns the object to the private variable, it checks first to see if it's already populated. If it is, it uses the instance that already exists. This enforces the pattern that there is always only one instance of the database object in the program. The access modifier of the database constructor is private, which prevents any external class from creating a new instance of the database object. This is key to enforcing the singleton pattern. Now that we've explored the singleton pattern's role in managing a single instance across an application, let's look at another essential pattern, the factory pattern. This pattern not only helps in creating objects, but also ensures that your code remains stable and adaptable even as changes are made. Let's investigate how this factory pattern works. In the factory pattern, instead of creating an object directly, your code asks a special method or class called a factory to handle the creation for you. This way your code doesn't need to worry about the details. The factory takes care of it, making your program more flexible and easier to manage. The factory receives some inputs, such as a parameter, that tells it what kind of object it needs. The factory then decides which specific type of object to create based on that input. By using a factory to create objects, the pattern keeps the code that requests an object separate from the code that actually makes it. This separation makes it easier to change or add new types of objects later on without affecting the code that uses them. To implement the factory pattern in C# for a notification system, you start by creating a public interface called iNotification. This interface will include a method called send, which takes a message as a parameter. Then you move on to the next step, creating two derived classes that inherit from the iNotification interface. One derived class will handle email notifications and the other will manage SMS notifications. Each of these derived classes implements the send method, which outputs the notification to the console. Finally, the developer creates a new class called Notification Factory that handles creating the email notification and SMS notification objects. They implement a method called createNotification that uses the iNotification interface as its type. This method also takes an input parameter called channel that tells the factory which type of notification object to create. Using this pattern, the developer can modify how the email and SMS notification objects are designed without impacting the code that requests them. The code that requires these objects just calls the createNotification method, passing in the channel parameter, and the factory handles the rest. Finally, let's explore the observer pattern, a key behavioral pattern that is crucial for managing communication between objects in complex systems. Imagine you're developing a user interface that needs to update in real time whenever the underlying data changes. This is where the observer pattern shines. It enables your system to respond dynamically to changes, keeping everything in sync without manual intervention. The observer pattern enables one object to automatically notify and update multiple other objects when its state changes. This pattern is particularly useful in systems where different parts must respond to changes, such as updating a user interface when data changes. Let's learn how a developer might implement this pattern in C# for a weather station application. To implement the observer pattern, you start with creating a public interface called iObserver. This interface includes a single method named update, which accepts a temperature parameter. This step lays the foundation for how observers will receive updates. The next step is to create the weather station class, which acts as the subject. This class manages a list of iObserver instances and is responsible for notifying all registered observers whenever there's a change in its internal state, like a temperature update. It has a private list member called observers that can hold iObserver interface objects. It also has a private member called temperature that holds temperature values. The developer creates methods for adding and removing objects from the observers list, as well as a method called notifyObserver, which iterates through each object in the observers list and then calls the update method on each one from the observer interface. This method passes the values set in the temperature member to the update method. The temperature member is set in the final method in this class called setTemperature. This method includes an input parameter called newTemperature, and the method sets the private temperature member variable to its value. It then calls the notify observer method. The developer then creates a concrete public derived class called phone display. The class will notify a phone interface of any changes in the temperature. The developer can use an app or a tool built into the phone to listen for this message. The developer also creates a concrete public derived class called desktop display to update any desktop apps or tools of the change in temperature. Each class is a derived class of the iObserver interface and implements the update method from that interface. The update method passes the temperature as a parameter and writes the temperature to the console in a message. To use the observer in the program, the developer creates new instances of weather station, phone display, and desktop display objects. Then they call the register observer method on the weather station object to register a new observer for each object. They pass in the phone display and desktop display objects as parameters when they call this method. Now, to update each display, they simply call the setTemperature method on the weather station object, passing in a new temperature. The iObserver interface, along with the subject class, will update all displays with the new temperature. These patterns are ways that developers can simplify code and make it easier to maintain. Design patterns provide developers with blueprints for creating well-formed, readable, and extensible code. In this video, you learned how to recognize and describe key design patterns like singleton, factory, and observer. These patterns are essential tools that help you write code that's efficient, easy to maintain, and built to last. Imagine you're an architect with a blueprint in hand. This blueprint outlines every detail of the house you're about to build, from the number of rooms to the placement of windows. But until you actually start building, that house just remains an idea on paper. In programming, classes in C# work much the same way. They're blueprints that define how objects will look and behave, but they need to be built before they can be used. In this video, you will learn how to implement classes and objects in C#. Let's briefly review what a class is and what they contain. A class is a blueprint or template that shares characteristics and behaviors for a group of related objects. Classes include properties. These are pieces of data an object holds, like a person's name or age. They also include methods, which are the actions an object can perform, such as displaying information. And finally, constructors are the special methods that initialize the object when it's created. With these key elements defined, let's now dive into the specific syntax used to define a class in C#. To define a class in C#, you follow a clear sequence of steps. First, start by declaring the class with an access modifier such as public or protected. This tells C# who can access the class. Next, you use the class keyword followed by the name of your class. This is how you identify the class in your code. Then you'll open the class body with a pair of curly braces. Inside those braces, you'll define the key components of your class, properties which store data, constructors which set up the class, and methods which describe what the class can do. Suppose a developer wants to define a person class with a property, name, and age, a constructor to initialize these properties, and a method to display the person's information. To define this class in C#, start by declaring it with the public access modifier, followed by the class keyword and the name person. Next, open the class body with a curly brace and close it with another curly brace at the end. Inside this body, add a string property named name and an integer property named age. Additionally, the class includes a constructor method with the same name as the class, which initializes the properties using two parameters, a string called name and an integer called age. To distinguish between the property and the parameter, the property names are capitalized and the input parameters are not. Finally, the class has a method called displayInfo, which writes the name and age to the console. Classes in object-oriented programming by themselves can't do much work. A programmer can't process data, interact with the user, or send API calls. In order for a class to do work, you need to create an object from it. This process is called instantiation. Let's see how that process works in C#. Instantiation comes from the word instance and refers to the process of bringing a class to life by creating a working version of it. Think of it like using a cookie cutter. The class is the cutter, and each cookie you create is an object. We call this working version an object. With this approach, you can create as many objects as you need from one class, just like you make multiple cookies from the same cutter. Now let's see how you can create an instance of the person class and start working with it in C#. When instantiating the person class, the developer first declares a variable of the type person, naming it neighbor. C# is a type-safe language, meaning all variables must be declared with a specific type, ensuring clarity about what they can store. The variable neighbor can only hold person objects. Now that the developer has declared the variable, they can create a person object and assign it to the variable. They use the new keyword, followed by the class constructor, which is a method and therefore followed by parentheses. The constructor requires a parameter with the type string for the name and a parameter with the type int for the age. In this case, they pass John Doe for the name and 30 for the age as parameters to the constructor. The neighbor variable now contains an instance of the person class, or a person object. Recall that the person class included the properties name and age. These properties were declared with a public access modifier. This means that they are accessible by code from the object once the class has been instantiated using dot notation. In what follows, you'll learn about dot notation and how to use it in C#. Dot notation is syntax used to access members of an object such as properties, methods, and fields. Once an object has been instantiated, developers can reference their public members using a period or dot, followed by the property or method name. Let's apply this syntax to the person object. Since the variable neighbor holds the instantiated person object, a developer can reference its members by using dot notation. Suppose after the object has been instantiated, the developer needs to update the person's age. They can set the person object's age value using neighbor.age, changing it from 30 to 31. The developer also can call any of the object's public methods using dot notation. For example, to call the object's displayInfo method, the developer would write neighbor.displayInfo, followed by empty parentheses. Classes in C# give the developer a lot of flexibility when working with code and helps them avoid redundancy. As an object-oriented language, classes are a foundational part of C#. In this video, you learned how to implement classes and objects in C#. We defined a class with properties, constructors, and methods, and instantiated objects from this class. Using classes is an important first step to building object-oriented programs. Using classes is an important first step to building object-oriented programs in C#. As you have learned, mastering objects, classes, inheritance, and polymorphism is essential for writing adaptable and scalable code in C#. We began by exploring objects and classes, the fundamental building blocks of object-oriented programming. You discovered how these components help create a well-organized, reusable code structure. Next, we explored inheritance and polymorphism, focusing on how these concepts improve your application's adaptability and scalability. We explained their roles and why they are critical to object-oriented programming. Then we used practical examples in C# to show how these concepts operate in the real-world programming situations, providing hands-on practice to reinforce your understanding. After that, we examined common design patterns in OOP, focusing on how they solve frequent development challenges. You learn the best practices for effectively applying these patterns in different situations. Finally, we worked on implementing classes and objects in C# through structured exercises, helping you build confidence and mastery in applying OOP techniques. Understanding these object-oriented programming principles is essential for building robust and efficient applications. Mastering these concepts in C# will elevate your development skills and improve your ability to create scalable, maintainable code. As software development has evolved, engineers continue to learn how to construct programs that are efficient, easier to maintain, and scalable. The common solutions that contribute to building software like this are called design patterns. Software engineers have created a set of patterns that all developers should follow. In this video, you will learn how to explain the importance of design patterns in object-oriented programming. Design patterns are reusable solutions to common problems that provide a standardized approach to architectural challenges in software design. They provide the developer with a template for how to solve an architectural problem when designing an application. Using a design pattern means following best practices. Because the pattern is common among developers, it helps improve how readable the code is, making maintenance easier. These patterns also make code run more efficiently. Let's explore a simple example. The singleton pattern is a design pattern that specifies that a class can have only one instance and should provide a single point of access to it that is available from anywhere in the application. This is useful for managing shared resources like a configuration manager or a database connection. Now that we've explored the singleton pattern, which helps manage the creation of objects efficiently, let's dive into other types of design patterns that address different challenges in software development. Creational patterns specify how developers should create objects in an application. The pattern focuses on writing code in a way that creates objects that are suitable to the situation in which they'll be used. For instance, even though creating global variables might be easier and less complex, overusing them could make an application less secure, consume more memory, and make code maintenance difficult. Creating a local variable that exists in a particular scenario and then is destroyed is a better pattern in general. Another category called structural patterns deals with how objects are composed and how classes and objects can be combined to form larger structures. Developers use these patterns to organize the relationships between objects and classes in a way that minimizes the impact of changes. One example of a structural pattern is the adapter pattern. Let's examine how this pattern works with an example. Suppose an object doesn't have an interface that is compatible with the interface of another object. Developers can use the adapter pattern to enable them to work together. If they later change the way one object works, they might only need to update the adapter, not the entire system. This minimizes impact to the system. For example, let's say you have an application with a square peg class and a round hole class. The round hole class expects objects to have a method for getting a radius, but the square peg class has a method for getting its width instead. The adapter pattern can help you write an interface so that these two objects work together. Now let's examine the final category of development patterns that focuses on how objects interact. Behavioral patterns focus on defining the rules and methods for how objects and classes operate together. They establish clear protocols for how tasks are divided among different parts of the program and how data flows between them. When developers effectively apply behavioral patterns, different components of the system will work together more efficiently, even as the system grows or changes. These three categories describe design patterns that developers should follow when creating software that's easier to maintain and that runs more efficiently. But developers might ignore patterns, so engineers have created tools to help software developers follow and enforce design patterns. Modern software development tools like Visual Studio Code are equipped with extensions that assist developers in writing code that aligns with established design patterns. For example, some extensions can analyze your code as you write and suggest refactorings that align with common patterns, such as converting repetitive code blocks into reusable functions or classes. Visual Studio Code's integrated development environment can analyze code and detect deviations from best practices, including the improper use of patterns. When they detect a deviation, they can alert the developer so they can make changes. These tools help developers write code that is consistent and adheres to the architectural patterns. Using a combination of tools and practices, developers should continually work towards writing software that adheres to accepted design patterns. This will make code easier to maintain and will help them create powerful systems that can more easily grow and evolve. In this video, you learned how to explain the importance of design patterns in object-oriented programming, including creational, structural, and behavioral patterns. By applying these patterns, you can write efficient, maintainable, and scalable code.